The question of when the world ends is not the only question. The question is what comes after. A lot of the time we think of cosmic endings as blasts or crashes, but the truth is stranger, colder, and much scarier. Imagine that there are no stars in the sky. A galaxy so big that even black holes look faint. A timeline that goes back so far that numbers don't make sense. But physics keeps moving forward. This isn't just guesswork for the sake of fancy. This is where science tries to look behind the curtain, because there might still be something there after the stars die. The atoms break, and time itself stretches to its edges. What if space falls apart? What if the machine breaks down? What if the end of the world isn't a loud bang, but a quiet word that lasts forever? This video takes us on a trip through time that goes back trillions of years to find out what is still there. There is no philosophy, not any myths, only science, math, and a strong desire to know what comes after the last frame. It's possible that the end of the world will be the start of something we've never even thought of. The heat death horizon. It doesn't sound that scary at first. Heat death might even sound nice, like the world taking a long nap. The truth is that it's one of the chilliest, darkest, and coldest ideas in all of science. It's not a big blast. It's not going down. It fades away slowly and can't be stopped. And most experts agree that heat death is the most likely way for the world to end. The universe began with a bang, the Big Bang, around 13.8 billion years ago. Ever since then, space has been expanding. Galaxies are moving away from each other. Stars are burning through their fuel, and everything that has energy is slowly, bit by bit, losing it. That's the key to heat death. Energy spreads out. Think of heat like money. Right now, the universe is like a party where some people have tons of money, stars, galaxies, radiation, and others have very little, cold, dark space. But over time, the rich give a little away, and the poor take a little in. Eventually, everyone has the same amount. That's called thermal equilibrium. No more winners, no more losers, just a flat, even nothing. In science terms, maximum entropy. And when that happens, nothing interesting can happen anymore. Why? Because all change, whether it's a plant growing, a rocket starting, or a star shining, needs changes in energy. You need heat to flow, particles to meet, light to shine. But in heat death, everything is the same cold, dead temperature. Stars burn out. Black holes get lighter. It gets dark, flat, and quiet in the sky. Always. First, stars use up their fuel. Big ones explode as supernovae. Smaller ones, like our sun, puff up into red giants, then shrink into white dwarfs. But even white dwarfs fade. After trillions of years, they cool into black dwarfs, dead stars that don't shine. The night sky will go dark. Next come galaxies. As stars die, galaxies go dim. Supermassive black holes at their centers may still devour matter for a while, glowing faintly, but eventually there's nothing left to feed on. Galaxies become ghost towns, filled with dead stars and cold dust. Then, even black holes begin to vanish. Thanks to a process called Hawking radiation, black holes slowly leak energy over time. It's incredibly slow. Big ones take over 1066 years to disappear. But in heat death, we're playing the long game. Eventually, they too will fade into radiation, leaving behind nothing but drifting particles. After all that, what's left? Just cold particles, neutrons, protons, maybe a few light rays stretched so thin by expansion that they're undetectable. These particles barely interact. They float in a universe that is vast, black, and totally silent. The temperature is near absolute zero. There are no stars, no planets, no light, no chemistry, just stillness. This is the heat death horizon, the final stage in the life of the cosmos. But even though it's called death, it's not sudden. It's not a cliff you fall off. It's more like sinking into a fog that never lifts. Every year the universe gets a little colder, a little quieter, a little less capable of supporting anything, and over trillions upon trillions of years, everything runs out of steam. But wait, what about expansion? The universe is still expanding and faster than ever, thanks to something called dark energy. This means galaxies are drifting away from each other faster and faster. Eventually, they'll be so far apart that even light won't be able to reach us from the next galaxy. Every galaxy will be alone, surrounded by a growing void. And then, even atoms will decay. Can anything survive that? Some ideas suggest yes. Maybe quantum fluctuations could shake things up in the future. Maybe black dwarf stars will detonate in one last cosmic firework. But in a heat death scenario, these are tiny sparks in an otherwise endless night. Why do scientists think this is the most likely way things will end? Because of the second law of thermodynamics. It is a fact of physics that entropy always goes up. Chaos is entropy. It's the idea that things get less organized over time. The ice melts, buildings fall apart, stars die. Plus, if you wait long enough, everything will end up in the same dull state. When entropy is at its highest point, there is no longer any structure, motion, or shocks in the world. Black dwarf supernovae, the last explosions. Long after the last red dwarf has gone out and the Milky Way has combined with Andromeda and turned into a cold smudge in the dark, there might be one last flash of light. Not from a star, not from another star, but from a black dwarf, which is a star that is dead and hasn't shined in a very long time. And in a cosmic twist that will happen a long time after the world went dark, it could explode in a supernova. Right now, our sun is a main sequence star, meaning it's still burning hydrogen in its core. One day, billions of years from now, it'll swell into a red giant, shed its outer layers, and collapse into a white dwarf, a hot, dense ember roughly the size of Earth, but with half the sun's mass. White dwarfs don't generate heat anymore. They just cool down over time, shining faintly like dying coals. White dwarfs cool very, very slowly. It takes trillions of years, much longer than the universe has existed so far, for a white dwarf to cool completely into a black dwarf, a frozen, lightless lump of carbon and oxygen. A black dwarf is something we've never seen. There shouldn't be any yet, in fact. It's not old enough for the world. But if you wait long enough, every white dwarf will turn into one. That's when things get surprisingly exciting. Black dwarfs are cold, dead, and quiet, but they're also very thick. And quantum processes never stop moving at their core. It's hard to imagine what will happen in 1032 or even 1037 years from now. Strange things start to happen. Some scientists say that the nuclei inside a black star might slowly join together, even though the temperatures are very low. This is called cyclonuclear fusion, and it is a type of nuclear reaction that is not caused by heat, but by very high pressure and quantum tunneling. Atoms are squished so close to each other that they join, even when it's cold. Over time, this fusion could build up iron in the black dwarf's core, just like what happens inside a massive star before it explodes. And eventually, that core could collapse. When the balance between pressure and gravity breaks, the black dwarf might go boom. One last supernova in a universe that had gone cold. Picture the scene. Everything has turned black, not a star. There is no heat. There has been no light for a very long time. Then, in the empty space, a single point pops up. A burst of energy, a flash of radiation, or a wave in space-time. Short, bright, and by itself. A supernova with a black star. The last fireworks show in a world that hasn't had any light in a very long time. In 2020, physicist Matt Kaplan wrote a study that suggested this very thing. He said that black dwarf supernovae could happen in periods longer than all of cosmic history put together. He said that the first one would happen about 10 plus years from now and keep happening for another 103 or 104 years. It's hard to imagine that happening so far in the future. But if it's true, it means that the end of the world might not be so quiet after all. These explosions would be rare, spaced across quadrillions of light years and trillions of years, but they'd be real. A final, delayed echo of stellar activity, a memory of fire in a freezing void. And they wouldn't just light up the dark. They'd also create elements, just like supernovae do today. Iron, nickel, maybe even heavier elements, flung out into a universe that has no stars to gather them. It's cosmic irony. The universe creates building blocks in an era where nothing is left to use them. So why does this matter? Because it shows that even in the bleakest version of the future, even in heat death, the universe still has surprises left. Black dwarf supernovae represent a kind of cosmic epilogue. Long after the main story has ended, these rare detonations whisper, "It's not quite over yet." These explosions might be the last luminous events in the history of the cosmos. After the final one pops, it's truly game over. No more light, no more change. Just darkness expanding forever. For now, black dwarf supernovae remain a theoretical curiosity. We've never seen one. We never will. Because they're so far in the future, we simply won't be around. But understanding them helps us sketch the timeline of cosmic decline. It's a reminder that decay takes time, and even the quietest, coldest objects can still carry within them the potential for one last blaze of glory. The final black holes, what lingers after everything else dies. One type of cosmic giant won't go away. even though the universe is dying. These are black holes, which are the strangest, strongest, and most stubborn things in the universe. Black holes will be around long after the stars go out. Galaxies move apart, and matter breaks down. They will be the last people playing the cosmic game for a while, but they too will die in the end. A black hole is formed when a massive star collapses under its own gravity. The core compresses until it becomes infinitely dense, a point called a singularity, surrounded by an invisible boundary known as the event horizon. Nothing, not even light, can escape from inside this horizon. From the outside, black holes look like dark, empty spheres, silent, cold, and unchanging. In the 1970s, physicist Stephen Hawking made a stunning discovery. Black holes aren't completely black. Thanks to the weirdness of quantum mechanics, they actually emit a faint glow known as Hawking radiation. It's incredibly weak, way too faint to detect with today's instruments, but it's real, and it has mind-bending consequences. This is how it works. Quantum physics says that even empty space is never really empty. There are simulated particles popping in and out of existence all the time. They might look close enough to a black hole's event horizon for one to fall in while the other gets away. The one that gets away turns into real radiation. It looks like the black hole is slowly losing energy from our point of view. It takes away mass from the black hole over time, which makes it shrink. There is Hawking radiation here. It also means that black holes can be evaporated over unbelievably long times. Not all black holes are created equal. The ones formed by stars, the kind scattered across galaxies, may take around 1067 to 10100 years to fully evaporate. But the supermassive black holes at the centers of galaxies, which are millions or even billions of times heavier than the Sun, will last much, much longer, up to 10100 years or more. That's a very long time. A number that is so big that it doesn't mean much in everyday language, but it's an important step in the big process of the universe's decline. Because black holes will still be around long after the stars die and the galaxies split up. They will be alone, very heavy, and slowly giving off their mass. As time goes on, the smaller black holes will disappear first, one by one. The bigger ones will slowly get smaller as time goes on. Hawking radiation speeds up as the black hole gets smaller. This means that at the very end of its life, a black hole might explode with energy, like a small fireworks show in the dark. Some scientists think that this last flash might quickly light up the area around the black hole, but there wouldn't be much left to see. Eventually, after all this slow fading, only a handful of the largest black holes will remain, scattered across an empty universe. They'll be completely alone. No stars, no planets, no galaxies. Just them, waiting out the end. Given enough time, Hawking radiation wins. The final black hole, perhaps a billion times the mass of the Sun, will shrink to nothing, vanishing into a final puff of radiation. At that moment, the last object in the universe disappears. No mass, no light, no structure. Just low-energy particles spread thin across a dark, frozen cosmos. What's left? Not much. Maybe a few stray photons, stretched by expansion until they're undetectable. Maybe some neutrinos, drifting endlessly with no one to interact with. But as far as major structures go, the black holes were the final chapter. The black hole era is a time in the past of the universe that could last for years because of their slow and stubborn fall. During that time, black holes will be the only things that can make the universe move. They'll take over the scenery while everything else goes away. The fact that they are no longer there shows a greater truth. No building lasts forever. The rules of thermodynamics and quantum loss say that even the most powerful and mysterious things in the universe have to follow them at some point. So, why does this matter? Because black holes are time bombs, just incredibly slow ones. They're the last engines of energy, the final storytellers. In a universe sliding toward heat death, they're the last things capable of doing anything, and when they're gone, nothing else happens. The timeline stretches on, but there's no more change. The universe becomes a blank page, flat, silent, and featureless. Proton decay and the death of matter. Atoms are often thought of as timeless. They are the building blocks of everything, including the stars, water, you, and this line. The proton, a strongly charged particle that seems impossible to break, is at the center of every atom. What if protons don't live forever, though? What if, after enough time, matter breaks down? If that's true, then the end of the universe won't just be cold and empty. It will be hollow, a place where atoms come apart, where everything solid becomes vapor, and where even the concept of stuff fades into memory. Atoms are made of protons, neutrons, and electrons. Electrons are tiny and fast, orbiting the nucleus like buzzing bees. Neutrons and protons sit in the center, tightly packed. For a long time, scientists believed that protons never die. In fact, we still haven't seen one decay. But some theories, especially those tied to grand unified theories, GUTS, predict that protons do decay. It just takes an absurd amount of time. How crazy is that? Give it at least 103 years. There are 34 zeros after that one. On the other hand, the universe is only 13.8 billion years old. If proton decay is real, we haven't seen it happen on a large enough scale to notice it yet. But if you wait too long, things might start to go wrong. In GUT models, the early world had one strong force that controlled all atoms. This force is called the strong nuclear force. These forces split apart as the universe cooled. But math shows that protons may have a very small chance of breaking down on their own into lighter particles like photons and positrons. Each proton only needs one every 10 years. Just think about how many protons there are in the world. It's about 108 bits. The universe has time, even if decay is very slow. It has a lot more time than any of us can understand. What do electrons do when they start to die? Atoms break apart. The atom loses its shape when a proton decays. The nucleus starts to shake. Electrons are no longer in motion around a center. Atoms and molecules split up. Solids leave the body. At the most basic level, the stuff that made stars, planets, rocks, and living things falls apart. Matter, which is made up of atoms, would eventually go away. It would destroy even white dwarfs, neutron stars, and black dwarf remains. Structures that had been resistant to entropy for a very long time would finally break down because of time, not because of heat or pressure. This would be the last breath of the degenerate era, a time in the past of the universe when the last solid structures break down into radiation and free particles. What's left after that? Only elementary particles, the ones that don't rely on protons to exist. This includes electrons, neutrinos, photons, and maybe dark matter if it turns out to be stable. These particles don't form atoms. They don't build stars. They just drift, like dust, across a universe that is quiet, expanding, and unfathomably old. If proton decay is real, it means that matter has an expiration date. It also means the universe's fate is more certain. No rebirth from old stars, no remnants to rebuild. Just a long, slow fall into absolute simplicity. The strange thing is that we've never seen it happen. For decades, experiments like Super Kamiokande in Japan have been looking for the sign of a proton breaking down in huge amounts of water. So far, nothing. That could mean that the loss of protons is not as fast as we thought. Protons might not break down at all, though. If that's true, some matter might live longer than black holes and stay as atoms in a cold universe forever. But most physicists think decay will happen, eventually. The math is elegant, the theories are strong, and the alternative, frankly, is stranger. A universe full of indestructible atoms roaming through endless darkness. So what does this mean for the big picture? It means that in the very distant future, 100 trillion years and beyond, we'll enter the era of disassembly. Black holes will still be around. Some galaxies will be gone. Stars will have long since vanished. But now, atoms themselves will start to rot, not in an explosive, fiery way, but in a quiet, ghostly fade. One proton at a time, one atom at a time. Gravitational wave afterglow. Echoes in an empty universe. Visualize a world with no planets, stars, or light. There would only be cold, dark space that goes on forever. Not an atom. There is no heat, not a galaxy. There is only quiet that goes on forever. After a while, there was a wave, a shaking. Space-time itself is being gently stretched and squeezed. It wasn't a sound or a flash. It was a gravity wave moving through space like the last note of a song that no one remembers. Even after matter and light have vanished, gravitational waves may still roam the cosmos. Gravitational waves are ripples in space-time caused by the movement of massive objects, like two black holes colliding, or neutron stars smashing together. When these events happen, they send out waves, similar to the way tossing a stone into a pond creates ripples. But instead of water, it's the fabric of space and time itself that ripple. These waves were predicted by Albert Einstein over a century ago as part of his general theory of relativity. But it wasn't until 2015 that scientists finally detected them using an incredibly sensitive instrument called LIGO, Laser Interferometer Gravitational Wave Observatory. That discovery proved something astonishing. The universe doesn't just move, it rings. And unlike light, gravitational waves aren't easily blocked or absorbed. They pass through stars, galaxies, even entire clusters of matter without slowing down. That means they can travel across the universe mostly undisturbed, carrying information from the most violent events in cosmic history. Let's go way ahead of time now. We are talking about a very long time from now, billions, trillions, or even quadrillions of years. There are no more stars. Several galaxies have moved apart. Black holes are slowly going away. An atom may be breaking down. The universe has reached its heat death, or maximum chaos. Even so, gravity waves may still be out there, moving slowly through space. Why? Because once a gravitational wave is produced, it keeps going. There's almost nothing to stop it. There's no light left to interact with, no matter left to absorb it. It simply stretches the fabric of space itself, slowly fading, but never quite disappearing. These ancient ripples, echoes from collisions that happened long before the last galaxy faded, could still be moving through the cosmos. Some might have come from the Big Bang itself, others from black hole mergers in the universe's more active days. These are the aftershocks of creation, still whispering across a universe that no longer remembers what it used to be. Of course, these waves do lose energy. Over time, they redshift, just like light. The expansion of the universe stretches them out, makes them longer and weaker. Their frequency drops, their strength fades. But here's the catch. They never vanish completely, at least not according to current physics. Like a bell that keeps ringing long after it's been struck, these waves can persist into near eternity. What does that mean? Gravitational waves might be the only things that move in a world that doesn't have any heat. Even though everything else has frozen or broken down, these small ripples could still change space on a very small level, stretching lengths just far enough for the rules of physics to notice. The waves may carry knowledge about things that happened a very long time ago, even if they are very weak. Some theorists even suggest that these gravitational waves might act as a kind of cosmic record, preserving the memory of what came before. In a universe where nothing else changes, that might be the only thing left that still moves. Because gravitational waves warp space itself, some researchers wonder if, under the right conditions, they could interact with one another. In other words, waves from different ancient events could cross paths, interfere, and leave strange patterns in the fabric of space-time. These patterns could become gravitational fossils, leftovers of motion in a cosmos that otherwise can't move. Could scientists of the future, if they existed, figure out what these trends mean? Could they read the last events of the universe from the lines of empty space that were shaking? It's an interesting thought. But the fact that these waves exist tells us something very important. The end of the world doesn't mean there is no sound at all. It means that everything is getting slower, fading, and going on longer. Nonetheless, not quite. Eventually, even gravitational waves may become so stretched by the expansion of the universe that they become undetectable. They may lose coherence. Their wavelengths could stretch beyond the size of the observable universe. But in some form, they would still be there, threads in the fabric of space-time, pulled thin but still holding together. Neutrino fog universe, the last particles standing. Some types of particles may still be around after the universe is over, after all the stars have died. The The galaxies have spread out and the black holes have gone away. They are very small, have almost no mass, and are very hard to find. Every second, they go through planets, stars, and even your body without leaving any marks. They don't shine, bounce, or talk to each other like regular matter does. They're out there, though. And when the world ends, they might be the only things that are left. These are the neutrinos, the quiet ghosts of the universe. Neutrinos are elementary particles, which means they're not made of anything smaller. There are three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They're created in high-energy environments like nuclear reactions, supernova explosions, and the early moments after the Big Bang. But once they're made, neutrinos rarely interact with anything else. That's because they're electrically neutral, have extremely low mass, and respond only to the weak nuclear force, one of the most elusive forces in physics. To detect a single neutrino, scientists have to use enormous tanks of ultra-pure water buried deep underground to shield them from other particles. And even then, millions pass through unnoticed for everyone that's observed. These particles are so aloof they could pass through a light year of solid lead without slowing down. But while neutrinos are hard to detect, they are incredibly numerous. Right now, trillions of them are flying through you every second. And the vast majority were created just seconds after the Big Bang, over 13.8 billion years ago. They're still out there, forming a kind of neutrino background, like the cosmic microwave background, but far colder and more elusive. Neutrinos might be moving through space even at the end of the world, when all matter has broken down and even black holes are gone. Why? None of the big events of physics really touch them because they are so light and don't play a part in them. They don't break down like protons do. They don't get pulled into stars that don't exist anymore. They don't fall into black holes that are no longer there. They don't stop. Think about a universe where neutrinos are the only particles. Not a light. There is no heat. Not much more than a faint cloud of particle ghosts moving through the dark. This is the neutrino fog universe, a time in the history of the universe when these almost forgotten particles are the only ones left alive. What would that world look like, though? To be honest, not much. Neutrinos don't make light bounce back. They don't stick together like planets or stars. They don't build buildings with gravity like normal matter does. It would feel like nothing at all if you could float through a world ruled by neutrinos. Not a glow, silence, never-ending silence. And yet those particles are still moving, still carrying energy, still obeying the laws of physics. They may not do much, but they are still there, the final fingerprint of a universe that once teemed with light, galaxies, and life. According to current models, the universe contains roughly 300 neutrinos per cubic centimeter. That's about 1,000 per cubic inch. Most of these came from the Big Bang and have been drifting ever since. As the universe expands, these neutrinos spread out even more, becoming cooler and slower. Over time, they redshift like light, losing energy as space stretches. But unlike photons, which eventually stretch so much that they fade into undetectability, neutrinos have mass. It's tiny, but non-zero. That means they'll never quite vanish. Even as their energy approaches zero, their mass keeps them as a real, measurable presence in the fabric of the cosmos. Do they matter in the grand scheme of things? It's what some scientists think. Some theories about the end of the universe include the idea that it might rely on whether particles like neutrinos can group together, make patterns, or interact with space in some small way. Gravitational interactions between neutrinos could create complex structures or patterns that we can't even imagine right now. These interactions could last for quintillions of years. It's also possible that given enough time, these neutrinos could interact with quantum fields, triggering new fluctuations or phase changes in spacetime. In a way, the universe's last active ingredients might not be stars or galaxies, but the invisible fog of particle ghosts that no longer have anything to bounce off. Could neutrinos spark the next cosmic cycle? Could they collide in just the right way to ripple space-time or kickstart a new inflationary event? We don't know, but if anything could, it would be them. Because by the time everything else is gone, neutrinos are all that's left. Frozen time, can time itself stop? What if time doesn't end with a bang, or even a fade? What if it stops? Not many people ask this because time seems to flow without stopping. The time goes by, stars move, and worlds spin. We get older, things take place. But what if time stopped moving in the very far future when everything is cold, dark, and quiet? In physics, time isn't some magical ticking thing separate from space. Instead, time is part of space-time, a four-dimensional fabric that includes length, width, height, and yes, time. Einstein's theory of relativity showed us that time is flexible. It speeds up and slows down depending on how fast you move, or how close you are to massive objects like planets or black holes. Time isn't always the same then. This is more like a setting on the control box for reality. Time is closely linked to entropy, which is a way to measure how chaotic or random a system is. The second rule of thermodynamics says that in a closed system, entropy always goes up. This is why things that are hot cool down, ice melts, and your room gets messy over time if you don't clean it. This link between entropy and time is crucial, because many scientists believe that the arrow of time, the reason we remember the past but not the future, is tied to the direction in which entropy increases. When things become more disordered, time moves forward. Now picture a universe where there is no order left in it. In this future, everything that could make things more chaotic has already happened. The stars are no longer alive. The galaxies have spread out. There are no longer any black holes. Atoms and particles, which are made up of matter, may have broken down into radiation. There are no energy gradients, heat flows, or processes left in the void. It is cold and still. If there's no more change, no processes unfolding, no entropy increasing, then from a physical perspective, time may have no reason to flow. In a universe where nothing can happen, does it make sense to say time is still moving? This is what some physicists call the thermal time hypothesis. It suggests that time, as we understand it, is an emergent property. It only appears to exist when systems change, when entropy increases. If the universe reaches a true heat death, where all systems are static, then the flow of time could effectively freeze. Not like pressing pause on a movie, more like the movie simply has no more frames to play. Wouldn't time still exist, even if nothing is happening? That's a valid question. According to relativity, time exists as a dimension regardless of what's inside the universe. But that's not the kind of time we experience. We feel time because stuff moves, changes, reacts. If there's nothing left to experience or measure those changes, then time becomes a meaningless backdrop, a coordinate with nothing in it. Clocks stop working in a heat-dead universe. Clocks don't work because of time. They work because of movement. Whether it's a pendulum swinging, gears turning, or atoms vibrating, all clocks rely on energy differences. But in a universe of maximum entropy, there's no energy left to power those processes. So even the most precise atomic clocks would eventually stop ticking. Not because they're broken, but because there's no energy gradient to drive them. There's no friction because there's no motion. No sound because there's no air. No memory because there's no information transfer. No future because nothing changes. From any internal perspective, if anything could still perceive, it would feel like being trapped in a single instant, stretched across eternity. Of course, some physicists argue that proper time, the time experienced along an object's path through space-time, never really stops. Even in the stillest universe, particles, if any remain, still exist in time. But if nothing can move or change, then nothing distinguishes one moment from the next. In effect, you can't tell time is passing, which is basically the same as saying it's not. So could time freeze? The answer depends on how you define time. If you mean a ticking clock, yes, absolutely. If you mean the abstract space-time coordinate, maybe not. But for all practical purposes, in a maximally entropic universe, time becomes irrelevant. There's no more sequence, no more before and after, just a static canvas of low-energy nothingness. It's possible that this is already happening in some parts of the world. Faraway galaxies move past our cosmic horizon as the universe grows. They are now so far away that light from them will never reach us. Entropic freezing might already be starting to happen in those faraway places, sort of like a local death in time. Not everywhere at once, but in waves that move slowly. Vacuum decay after the end. One final reset. It's possible that the world will end in quiet, or it could end with a snap, a wave that can't be seen or stopped that changes the rules of reality. It's not science fiction. Vacuum decay is a scary possibility that could happen long after the stars have died out, the black holes have disappeared, and time seems to have stopped. Everything could change in an instant, just when we thought the world was finally quiet. In modern physics, empty space isn't really empty. It's filled with invisible fields, like the Higgs field, which gives particles their mass. These fields determine the rules of our universe, how particles behave, how forces interact, and what kind of matter can even exist. But here's the twist. Those fields may not be in their most stable form. They might be sitting in what physicists call a false vacuum. Picture a ball sitting in a valley about halfway down a mountain. It seems stable, it stays put. But if there was a strong enough wind or a quantum change, it could push the ball down into a lower valley. The real void is that lower valley. It is the most stable state that can be found. It would be like that ball sitting in the shorter dip if our universe is in a false vacuum. It seems safe, but it won't last forever. If the universe ever tunnels from the false vacuum to the true vacuum, it would create a vacuum decay event, a sudden violent transformation of space itself. A bubble of true vacuum would form somewhere, and it would expand at nearly the speed of light. Inside the bubble, the laws of physics would be different. Particles might not exist. Matter might fall apart. Chemistry, gravity, even time could behave in completely alien ways. And there's no way to stop it. You wouldn't have seen it coming. It wouldn't hurt you. There wouldn't be any notice. As the bubble grew through space, it would smash atoms, stars, and even black holes to pieces. It's not a big blast. It's not a ball of fire. The old world is being erased by the new one. It could happen at any time and any place. Right now. It's not likely to happen, though. In fact, it probably won't happen for trillions or quadrillions of years, if ever. We've been talking about heat death and vacuum decay. This is what makes them different. A slow fade is heat death. The lights go out, things stop going on. But vacuum decay is a quick way to start over. It's like turning over the cards and starting over in the game of life. In the far future, after heat death has stretched the universe thin, after time has frozen, after black holes have whispered into non-existence, the stage could be perfectly set. A quiet, empty, cold universe might be the ideal place for a quantum fluctuation big enough to trigger vacuum decay. Without stars or galaxies to mask it, the decay bubble could grow unchecked, turning the dead universe into something brand new. Inside the bubble, everything would be governed by different physical constants. Maybe electrons wouldn't exist. Maybe gravity would be too weak to form stars. Or maybe, just maybe, the new vacuum would support a whole new kind of universe, with its own matter, stars, and life, completely unrelated to ours. In this sense, vacuum decay isn't just an ending, it's a transition. A passage from one version of reality to another, like a phase change in water, from ice to liquid to steam, except on a cosmic level. Does it matter if this has happened before? Some ideas say that the Big Bang we know today might have been a vacuum decay event in a past universe. Maybe another fake vacuum broke down into ours. And the universe we know now is what was left behind. A bubble that is still growing and full of space, time, and matter that didn't exist before. That would mean we're already in a bubble of pure ruin. The universe as a whole is the result of a single quantum event that keeps expanding. Of course, it could happen again in the far future. The Higgs boson, discovered in 2012, confirmed the existence of the Higgs field. When scientists plugged its mass into equations, Some versions of the math hinted that our universe might be metastable, balanced in a false vacuum. Not definitely, but maybe. That uncertainty is enough to make physicists uneasy. It means the end could come not just from slow entropy, but from a quantum trapdoor that opens beneath our feet. False vacuum collapse. Physics gets rewritten. Picture yourself living in a house that was built on a frozen lake. Everything feels strong. The floor doesn't make noise. There is no shaking in the walls. It stays stable until the ice melts. All of a sudden, your world is coming apart. There's something very scary about the idea that the universe we know is safe might only be temporary, balancing dangerously on a kind of cosmic ice sheet. Our universe is governed by quantum fields, huge, invisible energy fields that stretch across all of space. One of the most important of these is the Higgs field, which gives particles mass and helped shape the structure of our entire cosmos. This field has a certain amount of energy, and that energy affects the very fabric of physics. Now, energy in a field can exist in multiple states. Some are stable, true vacuums, like a ball sitting in the bottom of a valley. Others are metastable, or false vacuums, like a ball balanced in a shallow dent on the side of a hill. It feels stable. It looks permanent. But with just the right bump, that ball could roll down into a deeper valley, and everything changes. Physicists believe it's possible our universe is sitting in a false vacuum, a temporary energy state that only looks stable, but actually isn't the lowest it could be. And if that's true, the rules that make our universe possible, mass, gravity, atoms, light, are all built on borrowed time. A false vacuum collapse would begin with a tiny, random quantum fluctuation. Somewhere, out in the void, a small patch of space would spontaneously transition from the false vacuum to the true vacuum. This isn't an explosion. It's a reconfiguration of the quantum fields that define everything. The change would create a bubble of true vacuum that expands at the speed of light, devouring the old universe as it goes. Particles as we know them might not exist. Atoms might not form. Gravity could be stronger or weaker, or missing entirely. Space itself could warp differently. Time might behave in ways that don't make sense in our current model of reality. It wouldn't just be the destruction of everything. It would be the erasure of the rules that make everything possible. We wouldn't see it coming. Since the bubble expands at light speed, it would arrive instantly from our perspective. No warning, no alarm, just reality flipping off like a light switch. What would that time be like? We really don't know. Physics rules would be broken to the point where nothing we know could explain it. We don't even think about space and time as separate from this structure. Those might not exist as we know them if the vacuum breaks. It's not death that scares me about this situation. It's deletion. It's possible to wonder why fake vacuum collapse hasn't happened yet, if it is possible. After all, there are almost 14 billion years between the stars. The quantum dice should have rolled snake eyes by now, right? Okay, maybe not. It's very unlikely that something like this will happen. It could take trillions or even Google years, a 1 followed by 100 zeros, for it to happen. Or maybe it's already happened, but in parts of the universe that are so far away that we will never see the bubble appear. There's also a crazy idea that the Big Bang we are experiencing now might have been caused by a false vacuum collapse in an earlier world. When one world breaks down, it starts a phase shift that makes a new one with different rules. This view says that we are already inside a bubble that was made when another part of space-time collapsed. That means this isn't just the end, it's part of a circle, a quantum chain reaction of vacuums closing and new realities being born. All of this may sound like speculation, but it's based on real, current science. The Higgs boson's mass, which was found in 2012, is just on the edge of what is needed to make the world metastable. Math doesn't say for sure that we're in a fake vacuum, but it also doesn't say that we aren't. We always feel like we're on the edge of a cliff, not quite at the edge, but close enough to feel safe. What would a post-collapse universe look like? It might be incomprehensible. Perhaps it wouldn't support matter, or light, or space. Or maybe it would give rise to entirely new kinds of physics. new particles, new forces, new ways of organizing complexity. There's even the chance, however small, that such a universe could support a kind of post-cosmic evolution, one that we can't model or predict. False vacuum collapse is terrifying not because it's violent, but because it's final. Unlike black holes, heat death, or proton decay, which stretch out over unimaginable timescales, this event is instant and irreversible. It doesn't just end things, it replaces them. It could happen long after the universe has already faded into cold darkness. A quiet, still cosmos, no stars, no atoms, no light, could suddenly be rebooted, not by magic, but by a tiny quantum flicker buried in the heart of space itself. Dimensional breakdown, when space itself fails. Space is often thought of as a background, something calm, endless, and steady, a picture that can hold everything from planets and stars to time itself. What if space isn't really as solid as it seems? What if the very structure of the universe starts to break long after matter, energy, and even time have died? Not a big deal, not with a wave. But there is quiet as the dimensions start to fall apart. In physics, space isn't emptiness. It's a structure, a field, a set of properties that allows things to exist, move, and interact. It's shaped by gravity, bent by mass, and interwoven with time itself. General relativity tells us that space-time is a flexible, dynamic entity, not a void but a medium, and just like any medium, it may not last forever. On the smallest scales imaginable, Planck scales, space may not be smooth. Instead, it may be grainy, like pixels in a digital photo. According to quantum gravity theories, including loop quantum gravity and string theory, space-time could be made of tiny, discrete units. Below these scales, the idea of space as we know it stops making sense. It becomes something else: quantum foam, lattices, loops. In a dying universe, one that's cold, maximally expanded, and drained of energy, there may come a time when even these foundational building blocks start to destabilize. With no mass left to curve space, no fields to energize it, no time to sequence change, what holds the lattice together? Some scientists think that space is not a natural state, but something that happens over time. In other words, it only exists because there are other things. Things like matter, energy, entropy, and relationships are what give space its meaning. Space might not be a structure without them. It might just be a process. And if things change too much, like when the universe dies of heat, that phase could end. It would be like a liquid turning into ice and then back into air. In this case, though, the liquid is space itself. Space would not only get smaller in this case, it would also break up. The measurements used to figure out distance and position might not work anymore. Points wouldn't mean anything. The idea of geometry itself might lose its meaning. It wouldn't be here or there, just a quantum mess with no clear boundaries. There would be no place where things can happen. Truth is, we wouldn't. Once matter is gone and particles stop interacting, there's nothing left to measure space. No observers, no rulers, no clocks. The breakdown would be unobservable, not because it's subtle, but because observation itself would no longer be possible. It's the difference between an empty theater and a theater that ceases to exist. Some physicists link this idea to space-time discreteness, a hypothesis where the smoothness of space breaks down at the Planck scale. If, in the far future, quantum fluctuations or vacuum instability disrupt this underlying structure, then the space-time lattice could unweave. It's like tearing the threads from a cosmic fabric until nothing remains to hold the shape of the universe. When does that happen? Probably not anything. Not enough room, not enough time, nothing real. It is only a mathematical thing that doesn't go anywhere else. It is the end of all frames of reference. Dimensions can get smaller or disappear in some forms of string theory and hologram models. Some ideas say that the early universe had 10, 11, or even 26 dimensions, most of which are curled up so tightly that we can't see them. The world we live in now may have 3 dimensions of space and 1 dimension of time. What if those secret dimensions start to come loose, or the ones that can be seen start to curl? It's possible for dimensions to break down in two ways. They could completely fall or get jumbled up. In a world with no order, dimensions that aren't being used could become unstable. One could go on forever, and the other could crumple into a single point. Our comfortable 3D+1 model of spacetime could disappear, leaving behind a strange, broken field with no clear structure. Is this the end? Not quite. Because the rules of physics might still be able to find new patterns even in the end, if they are still around at all. Space might not be the same as we know it. There might not even be dimensions, but there's something else. A brand new base, a whole new way of being. Quantum resurrection. Can the void spark again? It's possible that the world will end in darkness, silence, and stillness, nothing but a frozen field of nothingness that goes on forever. There is no light, no matter, and no stars. But scientists can't sleep because they wonder if that nothing can come back to life. This idea is called quantum resurrection, the chance that even after everything dies, the universe could spark itself back into motion. No magic, no divine hand. Just physics doing what it's always done. Surprise us. It starts with something strange. In quantum mechanics, even nothing isn't truly empty. If you zoom in far enough, past atoms, past protons, past the smallest particles, you reach what scientists call the quantum vacuum. It's not blank space. It's alive with energy. Invisible particles pop in and out of existence. Fields fluctuate. Space itself trembles. This is the quantum foam, which is a rough sea below the real world. This foam could be the key to starting over. Even if there is no heat, motion, or time in the world, quantum foam might still be there. It's the deepest level of being. Some scientists say that if you give it enough time, a small area of this foam could change randomly into something else. And if conditions are just right, that bubble might expand. It might grow. It might even start inflating faster than the speed of light, just like our own universe did at the Big Bang. To put it another way, a whole new world could appear out of nowhere. It did not come from inside our world, but from the empty space it left behind. We think the world started out as a quantum fluctuation, which is a burst of energy in a very small point that grows into everything we see now. What's stopping it from happening again if it already did? Some theories even say it's easier for new universes to form in a dead cosmos. There's no gravity pulling things apart, no heat-breaking structures, just smooth, quiet emptiness. A perfect setting for a rebirth. This process is sometimes called baby universe formation. A tiny patch of space tunnels through quantum foam and inflates into its own new reality. From the outside, it's just a bubble. But inside, it could be a whole new cosmos, with its own time, laws of physics, galaxies, and stars. Maybe it wouldn't look like ours. Maybe it would have different particles, stronger gravity, or no light at all, but it would be real, and it would be growing. Could that new universe ever reach us? No. Once it forms, it separates from everything else. It pinches off from our universe like a balloon tied at the end. We'd never see it, never feel it, never even know it happened. Even if our universe fades into complete stillness, even if protons decay, time freezes, and space breaks apart, quantum foam might keep bubbling. And if it keeps bubbling, it keeps hoping for a spark. A chance twitch in the empty space could make something where there was nothing before the Big Bang. It's not going to happen because it should. However, in the language of quantum physics, nothing is not solid. It needs to change into something. That's why some scientists say the world will always be there. It just turns into a possibility, like dirt that is ready for a seed, like an open flame ready to be lit. Quantum resurrection isn't a fairy tale. It's a possibility buried deep in the rules of nature. And though it may take trillions or even Google years to happen, the universe has time. It always has time. Post-entropy structures. Can anything resist disorder forever? Entropy is the bad guy in the last act of the world. This is how energy spreads out over time. It's why stars die, black holes fade, and time keeps going forward. Entropy changes order into chaos, movement into stillness, and light into darkness. It wins in the end. In the bleakest version of the future, where heat death has frozen time and scattered matter into a thin, cold soup, some scientists wonder if anything could resist the pull of entropy. Could something endure? Could a structure, a pattern, a system somehow stay intact forever? This idea isn't about breaking the laws of physics. It's about finding the rare cracks where the rules might bend. Welcome to the world of post-entropy structures, the ultimate survivors of a dying cosmos. Entropy destroys systems by evening out energy. Hot things cool down, dense things spread out, organized things dissolve. A working machine becomes junk, a burning star becomes dust, a thinking brain becomes silence. But what if there are buildings that don't need energy to work? What if something exists not because it fights entropy, but because it doesn't care about it? Crystals of subatomic time. At least in theory and in well-controlled tests, time crystals are real. These structures move in a sequence not through place but through time. They are a new state of matter. They don't use energy to stay moving like normal matter does. They keep cycling without using any fuel. If you don't push it, it's like a swing that never stops. Now, time crystals we've seen so far only exist in lab conditions. They're fragile, tiny, and rely on very specific setups. But some researchers wonder, could natural versions form in the far future? Could time-based structures emerge in the last gasps of the universe, immune to entropy because they operate on a loop, not a slope? Then there are gravitational knots, mathematical structures in some theories of general relativity. These are twists in space-time itself, closed loops of gravity that might be stable even after matter and light are gone. They wouldn't need atoms or heat, just the curvature of space. Could they float forever in the emptiness? Quantum error-correcting codes are another idea. This one is strange and interesting. The holographic principle is one theory that says the universe saves data on the edges of space, like a universal hard drive. Quantum error correction could also protect that data, just like it does in digital files. This means that even if the universe breaks apart, its design might still be there, etched into the void in a way that can't be changed. If true, this means there could be parts of the cosmos that are informationally preserved even when physically destroyed. Not structures made of atoms, but structures made of logic, of relationships, of rules. It's hard to picture. But think about this. A single ripple will be left behind long after the last star has died and the last atom has broken down. A loop, an outline, a flash of code that keeps happening in the dark. It might not do anything. It might just be. But it stays. Simple is hard to break, not because it's strong, but because it's simple. Could living things ever ride these? In a sea of chaos, could intelligence, memory, or thought hold on to these safe islands in some way? We're not sure. There might be a future after decay, but it would need a base. A base. There may not be any solid ground left, and post-entropy buildings may be it. These things would not look like stars. They didn't shine. They refused to move. They would last, though, like physics skeletons that hold the last shape in a world that has forgotten how to hold anything. If there is a return in the future, like a quantum revival, a vacuum reset, or a spark from the foam, these structures may be the only things that remember the universe that came before. Dark matter's disappearance, when even shadows fade. Dark matter earned its name because it does not emit, reflect, or absorb light. It is literally dark. We discover its presence only by its gravitational pull. When we measure the motions of stars in a galaxy, they orbit at speeds that normal matter alone cannot explain. Something extra is adding mass, something we cannot see. This hidden mass is dark matter. Astronomers infer its existence by watching how galaxies rotate and how clusters of galaxies bend the light of background objects, creating cosmic distortions known as gravitational lensing. Every twist of a lens and every rapid swirl of a star whispers the same secret. Most of the universe is composed of something alien to our senses. What is dark matter made of? We don't know. The leading ideas go by mysterious names: WIMPs, or weakly interacting massive particles, axions, ghost-like particles with ultra-low mass, sterile neutrinos, cousins of the familiar neutrino, but even less social. These theories all share one thing. They propose a new kind of particle that barely interacts with ordinary matter. If dark matter is made of WIMPs, trillions of them might pass through your body every second without you ever noticing, as they barely bump into atoms. If it's axions, they could be so light that billions of them fit on the head of a pin, yet their collective gravity shapes entire galaxies. Scientists build deep underground detectors and powerful particle colliders to try to catch even a single dark matter particle, but so far they remain nothing more than clever guesses and experimental limits. While normal matter faces a bleak fate, stars burn out and black holes evaporate, dark matter may endure far longer. Protons, the building blocks of atoms, might decay over unimaginable timescales. Even the strong bonds that hold the atomic nucleus together could eventually snap. In contrast, dark matter particles may be fundamentally stable, surviving even the death of all stars and the evaporation of the last black hole. In a universe stripped of light and heat, dark matter could drift on in silence, a frozen relic of a bygone era. Picture a vast empty plain where once cities shone like beacons. Now only the faintest breeze of dark matter particles sweeps across nothingness. Imagine the far future, when the last star has flickered out and black holes, those final reservoirs of matter, have shrunk away through Hawking radiation. The cosmic landscape will be a cold, dark ocean with only dark matter to trace its depths. Without heat or light, time would stretch into a slow, silent eternity as dark matter particles coast through space, indifferent to anything, leaving no mark except their weak gravity. In this ghostly realm, the universe would resemble a desert under a night sky without stars, a cold expanse populated by invisible travelers. No galaxies, no planets, no living beings, just an endless echo of dark matter's gravity. But what if dark matter itself is not eternal? Some theories predict that dark matter particles could decay, albeit on timescales trillions of times longer than the current age of the universe. If a dark matter particle decays, it might release a small burst of radiation or transform into lighter particles that drift away at near light speed. Over eons, dark matter would slowly dissolve, its mass converting to energy and fundamental particles that spread across the cosmos. This decay would be so gradual and so faint that no living creature would ever notice the last dark matter particle giving way. It would be the quietest death imaginable, a stain of cosmic importance fading into oblivion without so much as a whisper. If dark matter decays, the collapse of cosmic structure would follow. The invisible scaffolding that shaped galaxies and dark matter halos would dissolve, leaving nothing to bind future generations of matter, though by then all normal matter would be gone anyway. Gravity would weaken everywhere as dark matter mass ebbed, and the last ghosts of structure would slip away. In the final chapters, the universe would be filled only with diffuse radiation and a few remnant particles. It would be the end, not just of visible matter, but of the very framework on which everything rested. The bones of reality would be erased. On the other hand, if dark matter does not decay, it becomes the universe's final inhabitant. In this scenario, the endgame leaves behind a cosmos filled entirely with dark matter, a shadow world without sunlight, heat, or chemical reactions. There would be no clocks, no change, no life, only billions upon billions of dark matter particles jostling each other with gravity alone, wandering through an unlit expanse. In this frozen sea, time would have no meaning, for nothing would ever happen. The fate of the Higgs field, mass in a dying universe. Discovered only recently, the Higgs field is an invisible energy field that fills all of space. It's everywhere. Right now, it's passing through you. And it's the reason particles like electrons, quarks, and protons have mass. Without the Higgs field, matter as we know it couldn't exist. Nothing could stick together. There would be no atoms, no chemistry, no life. The Higgs field might not last forever, though, just like space, time, and matter. What happens when the Higgs field starts to fade and the world ends in a cold, quiet way? Scientists found the Higgs boson in 2012. It is the particle that shows the Higgs field is real. One of the most important discoveries in physics was this, but when they checked the mass of the boson, they saw something odd. The number didn't match what some physicists had hoped. Instead, it hinted at a dangerous possibility, that our universe might not be truly stable. You see, fields like the Higgs want to be in the state with the least amount of energy. Picture a rock that is sitting in a valley. The pebble can be pushed into a deeper valley, though, if the valley isn't very deep. It's not safe if the Higgs field isn't in the lowest valley possible. This is what scientists call a false vacuum. It looks like it will stay put. In other words, the Higgs field could suddenly become less energetic. In that case, the rules of the world will change. Mass goes away. Particles cease to behave. Physics doesn't work. This collapse might happen randomly, triggered by a quantum fluctuation, a ripple in space, or even a leftover bubble from another universe. And once it starts, it spreads like a wave at nearly the speed of light. Inside that wave, mass doesn't work the same way. Protons and electrons might stop existing. Atoms could melt. Chemistry would die. It wouldn't be fire or ice. It would be unmaking. Picture the universe after heat death. It was cold and empty. There are no black holes or stars. They were only weak radiation and random particles. The Higgs field could start to move in this very flat and very quiet state, not from a big blast, but just because it wasn't stable. A slow fall into a pit of less energy. The universe doesn't just end when it slides. It changes into something that can't be recognized. If the Higgs field vanishes or transforms, then mass itself may stop being a thing. Particles could become massless, zipping around at the speed of light, unable to bond or slow down. The very idea of stuff would vanish. No more structure, no more building blocks. There's also the chance that the Higgs field will always be stable. It would last longer than stars, matter, and even black holes if that's true. There would still be things in it long after the universe stopped moving. In this form, mass would still be there, even if the universe was cold and empty. It wouldn't really matter, though. There would be nothing left that could have mass. Little bits of matter floating around in the dark. The Higgs field's outcome is important no matter what. If it stays alive, the universe's skeleton will be left behind, bare and quiet, but still whole. Everything will be different if it dies. Not only the things in the world, but also the rules that made those things possible. We're not sure which outcome is more likely. Our best equations say we're right on the edge, balanced between stability and collapse. It's as if the universe is walking a tightrope that stretches into infinity, and we have no idea if the rope holds up forever or gives way in the dark. The cosmological constant collapse. Could dark energy fail? The world is getting bigger. It's not news. Scientists are still not sure why the growth isn't slowing down. It's speeding up. As time goes on, galaxies are moving farther apart, like the dots on a sphere being blown up. There is no end in sight. What's driving that acceleration? Something we call dark energy, an invisible force that makes up about 70% of the entire universe. We don't know what it is. We just know it's there, pushing everything apart. And the simplest explanation for dark energy is a term Einstein once called his biggest blunder: the cosmological constant. The world is getting bigger. It's not news. Scientists are still not sure why the growth isn't slowing down. It's speeding up. As time goes on, galaxies are moving farther apart, like the dots on a sphere being blown up. There is no end in sight. Some theories suggest that dark energy could decay or change. It might not stay stable forever. It could shift, weaken, or even reverse. And if that happens, the entire universe could take a sharp turn, from quiet expansion into something far more chaotic. One possibility is that dark energy fades out. Slowly, over trillions of years, it just leaks away. If that happens, the universe's expansion would eventually slow down. Galaxies would stop accelerating away from each other. And in some scenarios, the expansion might even stop altogether. Would it be possible for the cosmic constant to not only fade, but also flip. Dark energy changes from being positive to negative in a situation called the Big Crunch. In other words, space stops pushing galaxies apart and starts pulling them back together. The growth stops, backwards. The universe starts to fall apart. At first it would be slow. Galaxies inch toward each other. But as time goes on, the pull gets stronger. Stars crash together. Black holes merge. Temperatures rise. Eventually everything, space, time, matter, light, crumples into a single fiery point. A reverse Big Bang. Or maybe something even stranger takes place. The cosmic constant doesn't go backwards. It moves back and forth. It moves back and forth like a heartbeat. Add more. Make a deal. Expand once more. The world turns into a living thing that keeps pulsing back and forth between creation and death. This is called a cyclic universe. Some models predict a kind of eternal rhythm, where each collapse is followed by a new birth. Not through a new Big Bang, but through the same force that once drove the cosmos apart. Suppose that this takes place very, very long from now. There are no more stars. The black holes are no longer there. There is almost too much entropy. After that, dark energy changes. At first a slow creep. Then there was a sudden drop. The stretching of space turns into a snapping back right away. The process wouldn't be easy. Those galaxies that are too far apart to see right now, they would come back quickly. Even space itself would get smaller. The web of space would knot and twist. In the end, everything could come together into one point, or it could split into many pieces in a way we don't fully understand yet. In some versions of string theory, dark energy is linked to fields that can roll down a slope. If the field reaches a steep edge, it can trigger something like a vacuum decay or dimensional collapse. In other words, a shift in the cosmological constant could act like a trapdoor, one that dumps the universe into a totally different state. A new vacuum, a new set of laws, a new universe. That means the cosmological constant could be the lever that decides whether the universe drifts into silence or resets the stage entirely. Why does this matter then? The growth is real. There is a real speed up. We don't know how stable the engine is though. It would never end. It might gasp and die. It could also go backwards and change reality. Space-time fracture. Does the grid shatter? We picture space as being smooth, clean, a stage that never ends and is always quiet, where galaxies move and stars spin. Space-time may be something else at its core though. This is not a soft cloth. It is a grid. Weave. A computer lattice made of the smallest pieces that can be found. The world might not be real. It could be made up of pixels. Einstein's theory of general relativity tells us that gravity is the bending of space-time. Mass curves it, and objects move through that curve like marbles rolling on a trampoline. It's a beautiful idea, and it works really well. Quantum physics and general relativity don't get along though. When the sizes get really small, the models start to fail. It gets fuzzy in space-time. Not sure. Strange. Physicists have come up with a novel idea to fix this problem. Maybe space-time isn't smooth after all. It could be made up of separate pieces. Quantum gravity is what we call this idea. In loop quantum gravity, for example, space is built from loops, tiny, tangled threads of energy. In string theory, particles are vibrating strings, and the universe has extra dimensions curled up in microscopic knots. Either way, the implication is the same. Space-time might be granular, like pixels in a screen, like Lego bricks holding up reality. What will happen if it breaks? Space-time might lose the compression that holds those loops and strings together in a world that is moving toward maximum entropy, which means it is cold, stretched thin, and low on energy. The building could fall apart. There could be holes. There could be problems with the grid. Getting rid of the code for the simulation is the same as getting rid of the screen itself, not just what's on it. Physicists have a name for the smallest unit of length, the Planck length, about 1.6 x 10 to 35 meters. You can't measure anything smaller, not because it's hard, but because it might be meaningless. Below this scale, space and time themselves may stop being continuous. It's like trying to split a pixel in half. You just get noise. If space-time fractures, we're talking about the collapse of this most basic structure. Not stars exploding, not particles decaying, but the loss of the canvas beneath everything else. Picture a movie in which every frame falls apart, not just the scenes, but the film itself. Something bad could happen. Some scientists think that if the grid breaks down, causal separation could happen, which means that cause and effect no longer make sense. Events would not be able to link up, not a sequence, not remembering, not a response. Moving would not be possible in this broken world, not because there is no energy, but because there is nowhere to go. Even the rules of logic might break down. Space-time is what lets math describe reality. Without it, the universe may not just be unobservable, it may become undefinable. What would this look like? Nothing. That's the point. Not blackness, not even emptiness, just non-being. The idea of distance, time, position, all gone. There's no center, no edge, no boundary, just the death of structure. Some quantum gravity models suggest that in the final stages of cosmic evolution, when everything else has decayed, the quantum lattice of space-time could undergo a phase transition. It could crystallize, or collapse, or dissolve into a different kind of geometry, one that doesn't support space or time at all. We might call that the end beyond end, when not only is there nothing left to see, but nothing left for seeing to be possible. So what remains? Perhaps fragments, stray patches of unbroken grid, like pieces of ice floating in an infinite dark ocean, but without a larger framework to bind them. They wouldn't connect, they wouldn't grow, they'd just drift, trapped in a timeless, spaceless purgatory. If the space-time grid falls apart, could it reset? Could new threads stitch themselves together into a new geometry? Could reality reboot? We don't know. But the fact that space-time could end, not by running out of energy, but by losing its own structure, is one of the most profound threats to existence we've ever imagined. The Planck remnant theory. Are mini black holes the endgame? After all the galaxies have broken apart, the stars have died, and time has sped up to the point where it seems like it will never end. There might still be one last type of building standing. Not stars, not atoms, no particles at all, not even the ones we know. But Planck remnants, theoretical leftovers of black holes so small and dense, they could be the final punctuation marks in the story of the universe. Black holes slowly lose mass as Hawking radiation draws it out of them. Even the biggest ones get smaller over trillions and trillions of years, releasing energy until they are gone. Or maybe not. His equations show that black holes get smaller and smaller until they disappear in a flash of energy. The Planck scale, on the other hand, is a real wall that this process hits. The Planck scale is the boundary of our current understanding of physics. Below it, space and time themselves may stop behaving normally. And if that's true, then there might be a limit to how far a black hole can shrink. Some physicists believe that when a black hole evaporates down to about the size of the Planck length, roughly 1.6 x 10 to 35 meters, it hits a floor. It can't shrink anymore. It stops radiating. It freezes into a stable, ultra-tiny object that refuses to die. A ghost of a black hole. This piece wouldn't have much mass, maybe the Planck mass, which is very small. It would still be curved and have all the information of the black hole it used to be, though. Like a data core that is very tightly packed and stores everything that fell into the hole. That's when things start to go wrong. Because in the final days of the universe, after even proton decay has erased normal matter, these remnants might still exist. No light, no motion, just unchanging particles of near infinite density, floating in a sea of quiet. Could they be the last pieces that make up the universe? It's possible. Planck fragments wouldn't break down like other particles would. Their light wouldn't shine. They didn't talk to each other. They would just keep going. They would be the only things left with any shape in a world where entropy has wiped out everything else. There are ideas that they might even be able to keep data, like black holes being hard drives. Don't forget about the black hole knowledge paradox. The thought that anything going into a black hole might be lost forever. which goes against the rules of quantum mechanics. Planck remnants offer a possible answer: that the information doesn't disappear. It just gets compressed, stored in the remnant, like data in an indestructible box. In a cosmos stripped down to its final bones, these black hole fossils could be the last traces of what used to be. They wouldn't glow or spin or collide. They'd just be silent, solid, and utterly alone. Some physicists argue that Planck remnants can't exist. They say it would break thermodynamics or require strange tweaks to quantum gravity. Others worry that if they do exist, there could be billions and billions of them left behind by all the black holes that ever lived. That's a lot of particles that can't be seen, felt, or stopped. It might even cause trouble in the universe right now. If Planck remains were common and steady, why can't we see what they do? Why don't they make the room full? Where do they hide? They might just be rare. Or maybe they only show up at the very, very end of the universe, when everything is just right and all the other rot is over. A few tiny pieces that don't change or break down may move through space forever, making it impossible to read. Not a part of the universe as it is now, but things that are left over from what it was. Some bold ideas say that Planck remains might be able to grow if the conditions are right, add more, even blow up into new worlds, with each piece becoming a new Big Bang. Tidal death, when gravity pulls everything apart. Most of the time, when we imagine the end of the universe, we picture a hushed collapse into silence. We think of a slow fade as stars run out of fuel and temperatures drop. But there's a far more violent possibility, a cosmic stretch so extreme that it tears everything apart. We call this scenario tidal death, or the Big Rip. Instead of slipping quietly into darkness, the universe could end in a convulsive taffy pull, stretching matter to its atomic and subatomic limits until there's nothing left but drifting particles. Right now, the universe is expanding. Galaxies drift apart as space itself stretches, driven by a mysterious force we call dark energy. And that expansion isn't slowing down, it's speeding up. Imagine a car on a highway that not only accelerates steadily but pushes harder on the gas pedal every second. If dark energy grows more powerful with time, its pull could overwhelm gravity at every scale, from galaxy clusters down to atoms themselves. The first signs of tidal death would play out on immense scales. Billions of years from now, galaxy clusters would give way. Groups of galaxies that once held tight under gravity would lose their grip as dark energy tears space between them. Galaxies would vanish beyond our cosmic horizon, their light stretched so thin that entire star cities wink out. The Milky Way, once majestic, would become a lone island drifting in an ever-widening void. As the expansion force grows, it begins to pick off smaller targets. Gravity can no longer hold galaxies together, so all the stars in our galaxy would fly away. Then gravity within star systems fails. The Sun might no longer keep Earth in orbit. Our planet would slip free and drift into an ever-darkening sea. Moons would break orbit around their planets. Planets would detach from their suns. In the final stages, the bonds holding everyday objects, mountains, oceans, even human bodies, would be too weak to resist the pull of phantom energy. But the true terror of tidal death lies at microscopic scales. As dark energy intensifies, it would tear molecules apart. Chemical bonds would break, dissociating water into hydrogen and oxygen. Then atoms themselves would come under siege. The electromagnetic forces that bind electrons to nuclei would be overwhelmed, and electrons would drift away. Finally, even the strong force inside the nucleus could fail. Protons and neutrons would dissolve, and quarks and gluons, the fundamental building blocks of matter, would be torn free. By the end, nothing more complex than a cloud of elementary particles would remain. This extraordinary outcome hinges on a single number in cosmology, the equation of state constant, symbolized by W. If W stays above 1, dark energy behaves gently, and the universe expands into a cold emptiness. If W equals 1 exactly, we end in a quiet heat death, a vast, dark and silent De Sitter universe. But if W falls below 1, a condition called phantom energy takes over. and the expansion accelerates without bound. In that case, there's no force strong enough to resist the pull of space. How quickly would this occur? In phantom models, the Big Rip can happen in a finite time. Depending on how far W lies below, 1, it might be tens of billions of years from now. Observers in an earlier epoch would watch as distant galaxies fade beyond reach. Closer to the end, star systems would dissolve millions of years before the final tear. A few months before the rip, the Sun's gravity would loosen its hold on Earth. A day before, Earth would fracture. Minutes before, atoms would unravel. And in the final moments, a fraction of a second, space itself would fragment, ripping the fabric of reality apart. Some physicists speculate that this cosmic tearing might trigger new phenomena. When space-time stretches to infinity, quantum fluctuations could seed the birth of a fresh universe. Like cracks in a windshield forming patterns, broken space-time might reorganize into a new cosmic structure. This idea suggests tidal death could be less of an absolute end and more of a transition, a chaotic reset that spawns another cosmos from the remnants of the old. Others caution that phantom energy may be impossible. Observations so far indicate dark energy might be constant, aligning with W equals sign 1. In that case, the Big Rip would never arrive, and tidal death remains an exotic thought experiment. The true nature of dark energy is still a mystery, and measuring W with precision is one of modern cosmology's greatest challenges. After the last star, the end of fusion forever. Our night sky is filled with beautiful stars that have been shining for billions of years. Ashes of old stars are used to make new ones, but nothing stays the same forever. Not even the light of the stars. Stars are fusion machines. They crush hydrogen into helium in their cores, releasing light and heat. Big stars live fast and die young, exploding in supernovae. Small ones, like red dwarfs, burn slow, lasting trillions of years. But even those will eventually run out of fuel. We are in the stelliferous era right now, which means that stars are being made. Galaxies are full of gas clouds, and every day, gravity shapes them into new stars. This won't last long though. As galaxies grow and crash into each other, their gas runs out, birth of stars slows down, and it stops in the end. Go ahead and skip ahead 100 trillion years. There are no more bright stars. Old red dwarfs have turned into cold, dead black dwarfs. Not any more fusion, not any more heat. As the last true star fades away, the world goes into eternal darkness. The end of starlight has come. But it's also the end of something more important, building things. Stars power things. They keep pressure and gravity in balance. They make things that are heavy. They make life possible, power worlds, and control the weather. The universe is still without them. After the last star goes, what's left? Black dwarfs, neutron stars, dwarfs white. A few stray planets might be floating around in the dark. But these are old things. It's cold, not working, not light sources, but remains from a long time ago. Even black holes don't shine, not unless they feed. And in a starless universe, there's nothing left to feed on. No new stars means no new energy, no new fusion. The universe stops producing complexity. Galaxies fade into ghost towns. All the brilliant dynamic interactions that once filled space with wonder go quiet. Well, can't stars come back somehow, you might ask? Could any gas that's left fall again? Could fusion happen again? It's not true, since the gas is gone. Either it has already turned into a star, or it was thrown into space when stars die. Too little, too cold, and too spread out is left. There isn't a time issue, there are funding issues. And all of them have been spent by the world. This era is sometimes called the degenerate era, when only degenerate matter, white dwarfs, neutron stars, black holes, remains. It's a phase of inactivity where nothing new can begin. Over trillions of years, white dwarfs cool to black dwarfs. Neutron stars drift through space, cold and silent. Rogue planets freeze solid, no warmth, no reaction, just drifting husks in an ocean of black. It's hard to overstate what this means, because the stars haven't just kept the universe bright, they've kept it alive. In their absence, time still ticks forward, but nothing interesting happens. No more chemistry, no more complexity, no more light to reveal what's left. It's not a sudden end of the world. It's the quietest finish you can think of. It's not instant, though. It takes a long time, longer than all of human history times 1,000,000. There are many, many years that you could live and still see stars. But in the end, the curtain comes down. What happens when the last star dies? The world turns into a graveyard, still getting bigger, it's still cold, following the rules of physics still, but it was totally quiet. That quiet is beautiful. It's not chaos. There is no damage. And that's what happens naturally when a universe runs out of fuel, reaches balance, and coasts into the void. Cosmic rays in a dead universe, the last lightning. The universe will look like it has nothing left to offer long after the stars have gone out and the galaxies are dark. Don't fuse. There is no heat, not a light. It looked like a frozen black ocean of nothing. While this cosmic graveyard is quiet, something strange might still be moving through the darkness. It could be a ghost from a long time ago. They're not rays at all, really. They're particles, protons, nuclei, and electrons traveling through space at nearly the speed of light. In our current universe, they come from wild places, exploding stars, colliding galaxies, black hole jets. When they hit Earth's atmosphere, they make tiny flashes, like invisible bullets zipping through the sky. But what happens to cosmic rays when the universe is dead? Surprisingly, they might still be out there. Even after the last stars flicker out and black holes shrink to whispers, cosmic rays could keep going. That's because once they're moving, there's almost nothing in space to stop them. No thick clouds, no magnetic fields, just a cold, empty highway that stretches forever. In the far future, the universe will be almost completely empty. But emptiness is exactly what cosmic rays love. Without gas or dust to slow them down, these particles can keep flying for trillions of years. Even longer. Some may have been launched billions of years ago, during galaxy collisions or star explosions, and will still be racing through space when everything else is gone. That makes them one of the last living things in a universe that is mostly dead. Like lightning flashing through a sky that doesn't have any life in it. However, cosmic rays end after a while. Their energy goes away as space gets bigger, not because something hits them, but because space is getting longer. Their wavelengths get longer every second. They change color, just like light does. High-energy particles turn into ghosts with low energy. They lose so much energy that they can't be seen anymore in the end. Imagine a world where even the strongest and fastest particles have been slowed down to the speed of sound. Proton shots that used to be very dangerous are now just gentle waves moving through space. They can't interact with anything because there's nothing left to interact with. What if some of these rays hit something, though? A black star floating alone in the dark. A piece of plank. A piece of reality that is still in one piece. It might not have a big effect, but it would happen. A sign of movement. A flash of power. Even though nothing else can move, this shows that something still does. Some scientists even wonder if the very last energy exchange in the universe might come from a cosmic ray. One final collision, one final reaction, a proton born in the core of a supernova billions of years ago, finally striking a cold remnant that's been waiting in silence. A tiny spark, and then nothing. There's also speculation that ultra-high energy cosmic rays could play a role in triggering exotic processes in the far future, maybe even disturbing dark matter particles or setting off tiny quantum events. It's a long shot, but in a universe where almost everything has stopped, even the smallest movement could be meaningful. It's for this reason that cosmic rays are not just particles. They bring messages, fossils of power, time capsules from when the universe was younger and brighter. They still send a message. The universe moved once, even when they're not very strong. Cosmos rays don't make new stars. They don't make the sky bright. But they are some of the last signs that things can move. That energy is still there somewhere in the deep void. Baryon collapse, do quarks fall apart? Everything we see around us, from the screens we stare at to the distant stars overhead, is made of atoms. At the heart of every atom are baryons, protons and neutrons, held together by the strong nuclear force. Those baryons themselves are built from quarks, bound tightly by particles called gluons in a theory known as quantum chromodynamics. Quarks are the final stitches in the fabric of matter, the last level of structure that gives atoms their identity and properties. For nearly the entire history of physics, protons have appeared indestructible. We have tested them and observed them, and they have endured for billions of years without showing any signs of decay. In the Standard Model, protons are stable, but this stability might be an illusion spanning no more than the current age of the universe, about 13.8 billion years. Grand unified theories, which aim to combine the electromagnetic, weak and strong forces into a single framework, predict that protons do decay, though on timescales so vast they outstrip our imagination. Some guts suggest a proton lifetime of 10 circumflex 34 to 10 circumflex 36 years, numbers so large they're hard to grasp. When a proton does decay, it falls apart into lighter particles. A common decay channel would see a proton transforming into a positron and a neutral pion, which itself quickly breaks into photons. The atom that once held that proton loses its positive charge and disintegrates. Free neutrons can also decay or convert into protons under certain conditions, so entire atomic nuclei can crumble. As protons and neutrons vanish, the familiar bricks of atoms give way to a soup of leptons, photons and neutrinos. The very notion of an element, hydrogen, carbon, iron, loses all meaning. Chemistry ceases. If baryons decay, quarks are next in line. The three quarks inside a proton or neutron might themselves tunnel into more fundamental particles or convert into even lighter forms that we have yet to imagine. Whether quarks vanish directly into energy or transform into exotic relics, the bonds holding together the last recognizable matter slip away. When this happens across the cosmos, it marks the final collapse of baryonic structure. The baryon era comes to an end. To place this in cosmic perspective, imagine the timeline of the far future. First comes the stelliferous era, where stars burn brightly. In roughly 10 circumflex 14 years, star formation will cease as galaxies run out of gas. The degenerate era follows, where white dwarfs, neutron stars, and black holes dominate, lasting up to 10 circumflex 40 years, as even black holes slowly evaporate via Hawking radiation. But protons, if unstable, begin their decay in the dark era, somewhere around 10 circumflex 34 years. By that time, all ordinary astrophysical objects are gone, and what remains is a cold expanse of dead stars and fading black holes. Yet within that emptiness, protons still roam, and then they collapse. The collapse of baryons dissolves atoms one by one. In a universe stripped of stars and galaxies, each atom flickers out in a silent act of quantum decay. The process is so slow and so rare that no single decay event would be noticed within any cosmic horizon. Over unimaginable spans, however, every proton and neutron eventually decays. Planets, dust, and interstellar gas vanish, leaving only the wisps of radiation and light particles produced by decay. After baryon collapse, nothing remains except a dilute fog of fundamental particles. Electrons, positrons, neutrinos, and photons, thinned across the vast cosmic volume. These ghosts drift without forming structures. They cannot clump, collide, or react to build anything new. Chemistry and atoms are history. Biology is impossible. There is no complexity left in this universe. Some theories suggest that even this final haze may not endure. In certain quantum gravity scenarios, particles could slowly lose mass or convert into pure radiation over even longer timescales. Yet for baryon collapse, the key boundary is passed when quarks, the last mutable building blocks, break apart from each other. After that moment, matter has no shape or form. It is pure energy and fundamental bits scattered in a void. Could anything survive this ultimate collapse? Perhaps exotic remnants remain. Tiny black hole relics with masses near the Planck scale, or stable particles predicted by string theory that outlive baryons by far. Neutrinos, with their ghostly interactions, could wander forever, but they offer no structure, just an endless trickle of particles. Even dark matter, if composed of stable particles, would continue to drift, largely unaffected by the collapse of baryonic matter. On Earth, experiments like Super Kamiokande in Japan and the upcoming Dune detector deep underground are searching for proton decay. They fill giant tanks with thousands of tons of ultra-pure water or liquid argon and listen for the faintest hints of a proton vanishing. So far, no signal has appeared, pushing the lower limit on proton lifetime higher and higher. Yet the absence of evidence is not evidence of absence. Our detectors simply cannot wait long enough to see a typical proton lifetime of 10 circumflex 35 years pass by. No watcher will ever witness the final quark unraveling. When baryons collapse, there will be no cameras, no instruments, no consciousness to mark the moment. Matter will not explode or flash. It will disappear gradually, like the last grains of sand slipping through an hourglass until the glass is empty. The universe will have lost its last physical identity, drifting into a state where only the laws of physics quietly dictate the behavior of particles in an infinite emptiness. The information dilemma. Does anything get preserved? The world is ending. The stars are no longer visible. Black holes are no longer there. Atoms have broken down. It's possible that time and space are also breaking down. But scientists still have one question. Does anything get remembered in the midst of all this cosmic collapse? Because in the end, it's not just about what survives physically. It's about whether the story of the universe, the information about what happened, where and why, can be preserved. Black holes are the ultimate destroyers. When something falls past their event horizon, it's gone. Or at least that's what we used to think. Matter, energy, even light, once swallowed, they seemed lost forever. The paradox then came up. Information can't be lost according to quantum physics. In physics, this is one of the most important rules. Particles' qualities, or the information that they exist, must still be stored somewhere, even if they are broken up. However, general relativity did not agree. Things get erased by black holes in their world. Get rid of it from the world. Gone for good. So which is it? For decades, scientists debated. Was the universe breaking its own rules, or were we missing something? Then came Stephen Hawking's wild idea. Black holes aren't perfect erasers, they leak. Through Hawking radiation, they slowly evaporate, one particle at a time, and, maybe, those particles carry traces of the information that fell in. While coffee is being brewed, the steam rising from the cup stores all of its history, the form, the heat, even the taste. But there's a catch. The radiation from Hawking seems random, nothing but noise. There are no clear signs that it holds the complicated data that the black hole used to hold. So there was more talk. Are black holes wiping out data, making a mess, putting it away where we can't see it? Black holes are gone, stars are gone, even baryons, protons and neutrons are gone. We're left with an ocean of nearly nothing. But here's the haunting thought. Maybe the universe still remembers. Some physicists think that information is never truly lost, just hidden in the quantum structure of space-time itself. Even when matter falls apart, the information that described it might be encoded in the entanglement between particles, the subtle vibrations of quantum fields, or even the geometry of the cosmos. Think of a burned book. The pages are burned up, but the ashes still have the bits of ink and paper in them. In theory, you could put the story back together if you knew everything about it. These are the ideas that some scientists have about the world. That the data from everything, every atom, every star, and every memory, will still be there after it all breaks down, stuck in the last quantum fields. Can't be read. Not easy to get to, but not gone. Others don't agree. As the world grows, some people say that knowledge is being split up too quickly, that Hawking radiation is really all over the place, that entropy, which means great eraser, wins in the end. Somewhere in that future, there is no record, nothing, no way to ever know what came before. just a bunch of particles moving through a quiet space. Because humans are creatures of memory, we archive, we document, we write stories and histories and data logs. The idea that the entire universe's history might be erased feels wrong, not just scientifically, but emotionally. But there might be a third choice. It's possible that the data is not stored in the particles or the fields. It could be the world, that everything, the shape of space, the values of basic constants, and the small changes in quantum mechanics, is shaped by what came before. Like footsteps that are now solid rock, even though the person who left them a long time ago. Also, in a future that can't exist, a new world might form, and somewhere in its DNA is a trace of the one that came before it. A thought, not in the way we think about it, but in this way, space-time curves, in the whisper of everyday things, in the laws of science that control what comes next. The silence of light. What happens when photons freeze? Imagine a world with no planets, stars, fire, or light. It was nothing but cold, dark space. It might sound like the end of the world, but light is still moving through the empty space. Even when the cosmos has collapsed into silence, some light, photons, will still be traveling. Not from stars or flames, but leftovers, ancient echoes, radiation from long-dead stars, remnants of cosmic events that happened trillions upon trillions of years ago. As the universe expands, space itself stretches, and when space stretches, light stretches too. Photons lose energy, their wavelengths get longer, they shift toward the red end of the spectrum, a process called redshifting. Right now, the universe is full of light, not just from stars, but from the cosmic microwave background, the afterglow of the Big Bang itself. This radiation has been stretched for nearly 14 billion years. It started as intense white-hot energy. Now it's microwave radiation, gentle, cold, fading. Fast forward a few trillion years. That background light? It'll be so redshifted, its wavelength will be longer than galaxies, then longer than the universe itself, until it fades into something that's not quite detectable anymore, a photon's ghost. Technically, it's still there. However, with almost no power. This is what takes place when the light stops, not the way that water freezes. There's no ice. There was no quick stop, just a slowing down, a softer state, a fade. But not until photons are stretched so thin that they can hardly be seen in space. All the starlight ever emitted, the glowing leftovers from galaxies, the radiation from black holes and dying atoms, it's all headed the same way. Every photon, no matter how energetic it began, will lose steam as the universe continues to stretch. And the best part? It can't be stopped. At this point in time, there is no pressure. There are no walls. There are no atoms to hit. I can't bounce off of any magnetic fields. Photons just fly away. Always. They get longer, they change color, they drain. They never crash, though. That means the light we send out today, every radio wave, every laser beam, every flicker of your flashlight, could one day become a strand of the final cosmic tapestry, an ultra-faint thread pulled across unimaginable distances. Eventually, those photons will redshift beyond the observable universe. Their wavelengths will be so stretched that no detector, no technology, no matter how advanced, could ever spot them. They'll still exist, but they'll be undetectable, like music with no air to carry it. Some scientists call this the photon death horizon, the point at which light still exists, but can't interact with anything, can't heat, can't reflect, can't transfer energy. It becomes light in name only. In the heat death of the universe, it's not just stars that vanish. It's the ability for light to do anything at all. Photons may be eternal, but their purpose, their spark, isn't. You could have 1 trillion photons in a cubic mile of space, but if they're too stretched, too cold, too red, they're invisible. They don't light up, they don't warm, they don't matter. Chronon theory, time in quantum packets. Time feels smooth. It goes, the seconds go by, the clocks move, What if that's just how it feels and not how things are? What if time doesn't go on forever? What if it comes in tiny pieces that can't be put together again, like movie frames or screen pixels? What if we turn time into numbers? In physics, we've discovered that many things we once thought were smooth are actually made of little chunks. Energy comes in quanta. Light, made of photons. Space, maybe built from tiny loops or strings. So why should time be different? One idea about time is that it is more like a slope than a smooth river. It's not like the world flows from one moment to the next. It jumps from one tick to the next, from frame to frame. It's possible that each of those jumps is as short as the Planck time, which is 5.39 x 105 seconds, the tiniest amount of time that the rules of science can describe. That's not possible. That moment can't be split in half. Time doesn't mean anything below that. Now, in the beginning of the universe, during the Big Bang, time moved very quickly. There was energy everywhere. There were events every Planck time. Bang, bang, bang. A rush of making things. But what happens when everything slows down? When you have no more power, no more moving, when there is no more change and entropy is at its highest? Do you want the clock to stop? Proton theory opens up a wild possibility that if time is made of discrete steps, then there must be rules for when those steps happen. If no events take place, no particles move, no fields change, then maybe the clock doesn't tick, it just sits. Those words would mean that time doesn't move on its own. When something else takes place, it will only happen. To put it another way, no change, no time. And in a world that is long since dead, there isn't much that can be changed. Don't fuse. It doesn't work. Not an atom, not a scratch. There are only a few cold particles floating through space in silence. Proton theory suggests time could become granular and slow. In the same way that heat death silences light and movement, it could also slow the passage of time to a crawl. Eventually, the moments themselves might stretch so far apart that they become meaningless. This is where time stops being time, a place where time itself is no longer time. There are quantum bits in time which makes the world look like a computer setup. Each event is a frame, every move is a bit. Everything that has ever happened, like every atom that moved and every photon that went, could be stored in this string of ticks. And if the universe ever resets, those ticks could provide a kind of code, a script, a memory of everything that came before, written into the structure of time itself. What will happen when there are no more ticks? In one future form, time is stretched so far that there are no breaks between chronons. There will never be another time like this. The movie is over, and the projection has turned off. Time goes backwards in another form. The chronon count starts over. A new start. Tick one of a new video game. Time might be made of chronons, but we don't know for sure yet. It's just a guess. The far future of the world will be even stranger if it turns out to be true. There is a chance that the world will not end when it runs out of light, matter, or space. It could die because time is running out. Black hole chemistry. Can entropy be recycled? Strange things happen in black holes. That's something we've said many times. They are places where gravity is so strong that not even light can get away. They bend time, eat matter, and wipe out everything that falls inside. This idea comes from a surprising corner of theoretical physics. Scientists once believed black holes were simple, just a point of mass surrounded by an event horizon. But the more we studied them, the more complicated they got. Black hole thermodynamics is the idea that black holes have temperature, pressure, and even chaos, just like other things. They don't just lead to nowhere. They're living things that respond to change and give off energy, like kettles that are cooking. The catch is that black holes seem to follow the rules of science. That's right. Some physicists now describe black holes using equations that look eerily similar to chemical reactions. They have states. They have phase transitions. Some even compare them to molecules with horizons that can change shape and structure depending on the conditions. Could black holes be the only places where entropy still moves in the far future, when all matter has broken apart, all light has faded and all atoms have broken down. Hawking radiation is the way that black holes give off energy right now. They slowly disappear, dropping mass until they are gone. They get warmer as they shrink, though. They send out waves faster. In their last moments, they burn with a lot of force. The thing is, though, they're not just losing power. They are working on it, like an oven that makes data burn. That's where the relationship comes in. Things don't just disappear when they fall into a black hole. New studies suggest that the black hole's event horizon may store its information, or identity, in quantum terms. It is processed by the black hole and sent out in bits and pieces through radiation. What happens when there are no more living things but black holes? In a world that is dark and frozen, they might be the only ones who can recycle entropy by taking in random particles, processing the information they carry, and sending it out as soft radiation, like space trash bins. They were not going to fix anything, but they would keep chaos going. Some black holes may not behave like single particles, but like molecules, composite systems with multiple charges, bonds, and even internal structure. Some theories talk about black hole chemistry, with different types of black holes transitioning between states based on pressure and temperature. Could these small differences let black holes make patterns that are hard to explain? Are there ways for black hole systems to react with each other? Could there be a kind of black hole chemistry happening in the universe's last age? It would be slow, quiet, and consistent. We're not sure, but it's possible. Black holes don't just sit there, they change over time. They might join together, they might give off radiation, they might mix with the particles that are still there. They could even talk to each other, trading entropy like molecules in a cold soup in space. Not in terms of people, not in the scope of the galaxy. This is about the stuff that doesn't really go away, even when everything else does. It's about chaos and knowledge. There may be one last Hawking explosion before the last black hole disappears. That could be the last chemical process in the universe. The causal horizon. What happens beyond reach? The universe was small and hot at first, with everything close together and linked. But space has been getting bigger since the Big Bang, not only growing, but also speeding up. As time goes on, galaxies are moving farther apart, like the dots on a balloon that keeps getting bigger. And if this growth keeps going on forever, strange things start to happen. Parts of the universe become impossible to reach, always. This is called the causal horizon, a cosmic boundary that tells us how far we can see, influence, or interact with. Anything beyond that line, it might as well not exist. Because no signal, no photon, no gravity, no particle can ever reach us from beyond it. Right now, our observable universe is about 93 billion light-years across. But most of that stuff, it's already speeding away faster than light can travel. And as dark energy continues to stretch space itself, more and more galaxies will slip beyond our causal horizon. That sounds like the end of the world, right? It means that there is no chance of being alone. Right now, we live in a very nice part of space, a huge number of galaxies, a huge number of stars. But a very long time from now, say 100 billion years from now, we'll be completely alone. You will no longer be able to see other worlds. The Milky Way and Andromeda will have joined together to form our own neighborhood group. The universe doesn't get smaller, but the way we can get to it does. It's like living in a city where every building is slowly being pulled away faster than you can run. Eventually, the lights of your neighbors fade, then their voices, then the memory of them, until you're in a city of one. Because the causal horizon doesn't just hide things, it cuts them off. Particles beyond that horizon can't affect us anymore. Gravitational waves can't reach us. Information can't travel in. Even the vacuum energy on the other side becomes irrelevant. In a very far future, the world is made up of many small, separate islands. Now that the galaxy groups are stuck together, each one is its own little physics bubble. Nothing to do, not talking to anyone, no shared fate. There would be nothing to see if you looked into space. Not a star, not a galaxy. It was just the silence of darkness. This takes place a long time before heat death, proton decay, or black hole evaporation. One of the first signs that the end has already come. The creepy part comes next. We've been losing galaxies since the universe began to speed up, which was about 5 billion years ago. Over our causal range, thousands of them have already disappeared. Because their light hadn't stopped reaching us yet, we didn't notice. But soon, the last rays will come. After that, there was quiet. What happens to the things that are past our horizon? It keeps going, keeps getting bigger. It might change over time. It might break down. But it's gone for us. Always. It can't be taken back, and in the most fantastic future, nothing will be possible. All power, everything matters, a whole building. One day, even the last particle of the last atom might be split in half by a line that it can never cross. It's not possible for the world to end. It breaks apart easily. Frozen expansion, when the universe outgrows itself. The world is getting bigger, not like a child or a tree, but like space is stretching and pulling everything apart. This growth was slow at first. There was still more gravity than air. There could be galaxies. Stars could group together. The universe had order. Around 5 billion years ago, a force called dark energy took over, and the growth sped up. In the far future, this speeding up will not be able to be stopped. The world won't just get bigger. It's going to get too big. When you think of expansion, picture galaxies moving away from each other. Not because they're flying through space, but because space itself is growing between them. Like ants on a balloon, you don't need to walk to get farther apart. The balloon does it for you. Think about this bubble gradually getting bigger and bigger over time. The space between galaxies gets so big that photons, which are tiny bits of light, can't cross it anymore. In an instant, you're a part of a huge web of stars and groups. 1 minute, you're with no one else. Everything else is now too far away to reach. It's not science fiction. It's taking place already. Right now, there are galaxies whose light will never reach us, no matter how long we wait. A cosmic event horizon is a kind of line that they've already crossed. Beyond this line, growth goes faster than the speed of light. In a world where speed is constant, the distance between particles gets so big that they can't connect in any useful way. Gravity gets weaker. Some light stretches, drops in temperature. The world turns into a thin, cold cloud over time, a region with no light. This is what we mean when we say frozen growth. Not just that things are far apart, but that the expansion has broken the ability for anything to affect anything else. It's the death of contact, the end of closeness. In such a universe, physics still exists, but it becomes local only. Nothing spreads, nothing moves fast enough. There's no more cosmic communication, no feedback loops. Each region is like a drifting island in an ocean that never ends. Galaxies stop merging. Star formation halts. Even black holes, drifting too far apart to ever collide, live out their long lives alone. Matter becomes dust. Dust becomes background radiation. Radiation stretches until it, too, disappears into silence. You might wonder if this isn't just heat death. Not really. When everything hits maximum entropy, or total balance, there is no more energy that can be used. On the other hand, frozen growth is about math. Being so big that chaos can't even be shared is what it's about. Every part of the universe finds its own peaceful balance and is cut off from the rest. What it's like is a million separate heat deaths, each one stuck in its own fate. Dark energy reversal. Could expansion collapse? Black holes have been in charge of the universe for billions of years. It's the unknown force that's speeding up the expansion of the universe, which is why galaxies are moving farther apart at an increasing rate that shows no sign of stopping. From what we can tell, dark energy is always there and will always be there. What if it's not? What if the force that's pulling the world apart changes direction all of a sudden? What if one day growth stops and folds in on itself? With this crazy thought, dark energy could be turned around. The future of the world would be turned upside down. Let's start with what we know. Dark energy currently makes up about 70% of the universe. It's not a substance like gas or dust. It's a property of space itself. Wherever there's empty space, there's dark energy. And the more space there is, the more dark energy exists, which means more expansion, which means more space, and so on. It's a feedback loop with no breaks. We don't know why dark energy exists, or how stable it really is. We just know it's there, for now. In some versions of physics, dark energy isn't constant. It's a field, a slowly evolving energy that could rise, fall, or even flip signs over time. In other words, the same force that's currently pushing the universe outward might someday start pulling it inward instead. Things that used to be far apart start moving toward each other. The huge cosmic web gets smaller, the temperature goes up, space gets smaller, time gets shorter, and finally, it all falls apart into a single, unbelievably complicated point. The Big Crunch is like the Big Bang turned around, a complete go-back in time in the universe. It was like all matter, energy, and space itself came together in one big bang. But that's only one version. Some ideas say something even stranger is going on, a bounce. Dark energy flips in these models, which leads to breakdown. Then, just as things are getting the tightest, a new Big Bang happens. A new universe starts to grow. A new cycle starts. The idea that the universe lives, dies, and is born again and again is called the circular universe theory. Each bounce could create a universe with different physics, different constants, different outcomes. Maybe some cycles produce stars and life, maybe others don't, but the process never ends. The world beats like a heart. Take a deep breath in, let out a breath, add more, break down, start over. But let's go back to our world. Is this change likely to happen? Perhaps, perhaps not. From what we know now, dark energy is solid. It looks like the equation of state parameter, that unexplained W number, is close to -1. That points to a never-ending expansion, heat death. But space is still very new. We also don't have exact numbers. Some models, like those involving quintessence, propose that dark energy is dynamic, not fixed. It could decay, it could reverse. It could even rupture the structure of space-time in a phase transition. If dark energy reverses, then everything we think we know about the future is wrong. The silence and stillness of heat death. Replaced by motion, gravity returns, structure reforms. The universe doesn't fade, it falls. We might not be able to see it coming. Behind the cosmic limit, a change could begin slowly. The change might not be seen at first, until galaxies start moving in the wrong direction, until the light starts to shift from red to blue, until it feels like the world is coming back instead of running away. End of the elements. When atoms can't hold together. Hydrogen, oxygen, carbon, and iron are some of the elements that make up everything we touch, breathe, and know. Molecules, stars, planets, and people are all made of these elements. To put it another way, they are the building blocks of complexity. But what if the elements go away one day? It's not just decay, not just fade, but unwind. So much that atoms can't exist anymore. Right after the Big Bang, only the lightest ones existed, hydrogen and helium. Then, inside stars, fusion create heavier elements, carbon, oxygen, nitrogen, all the way up to iron. When massive stars exploded, they forged even heavier ones, gold, uranium, lead, and scattered them across the cosmos. These atoms made up the foundation of the world. That's how science was made possible. They made it possible for people to live, but not even atoms last forever. In a very long time, the fusion plants will close. The stars will disappear. There will be no more deadly war. That means that new parts will not be made anymore. There will be a slow fall. At first, it'll be subtle. The universe cools. Galaxies go quiet. Atoms still exist, but they are spread across trillions of light years, too far apart to collide, too cold to react. Elements remain, but chemistry ends. Then there is proton decay, which is the slow, long death of atomic atoms. It is thought that protons have a half-life of about 10 years. That is a 1 followed by 34(0)s. It's way too long to imagine. On a cosmic level, though, one more tick on the clock. Protons break down into lighter particles like photons and positrons. Atoms break apart. The core goes away. Electrons move around freely. Atoms are dying right now. Not any more order. Not any more molecules. Not any more parts. White dwarfs, neutron stars, and black dwarfs are some of the matter that is the most resistant to breaking down. Eventually, they will turn into radiation and basic particles. That's not all, though. Strong nuclear force holds quarks together inside protons and neutrons. But as the world continues to grow, this force may weaken. There are ideas that even quarks might break apart in the very far future, either into smaller unknown pieces or into pure energy. The chemical table isn't just going away, it's taking off. After that, the world will be in the post-elemental age. What's left? Neutrinos, electrons, and photons are spread out in a thin fog. There might be a few dark matter remnants, if those particles are really solid, but there's nothing that can bring people together, build, or shine. Even light itself is stretched beyond recognition. Photons redshift until their energy becomes too low to interact with anything. Space keeps expanding. The few particles left are too far apart to ever meet. In this world, nothing is going to stay together. Not an atom. Nothing there. It doesn't work. Simple things only. Complete and unchangeable simplicity. The strange thing is that this simplicity isn't just about losing things. It's also about being clean. The universe has lost some of its layers after being made up of stars, life, crashes, chaos, and complexity for billions of years. Particles and reality without any memories are all that's left. You could say the elements had their time. They built everything. They burned bright, and then they stepped aside. So will the universe rebuild? Not unless something radical happens. Without atoms, there's no fusion. Without fusion, there's no stars. Without elements, there's no tools to begin again. Quantum lattices at infinity. Is the end pixelated? If you zoom out enough, the universe will look smooth. Beautiful swirls are made by galaxies. Light moves in beautiful waves. Space is curved in known ways by gravity. That being said, what happens if you zoom in really close? Like, really close. You may discover that the world isn't smooth at all. Pixels could be in it. This is the world of quantum lattices, a mind-bending possibility that, at the deepest level, space and time are built from tiny, indivisible units. Not continuous fabric, but a grid, a cosmic scaffolding. And in the end of everything, when matter has vanished, light has faded, and time itself stretches to infinity, that lattice might be all that remains. In current physics, there's something called the Planck scale. At this scale, around 1035 meters, our normal ideas about space and time stop working. Distances become fuzzy, time becomes uncertain. You can't measure anything smaller because measurement itself loses meaning. To fix this, some scientists have proposed that space is made up of quantum units, a lattice of cells like pixels on a screen. The theory goes by many names: loop quantum gravity, spin networks, causal dynamical triangulation. But the core idea is the same. In the very far future, when there is no more change and all processes have stopped, there may still be this system holding everything together. Not tiny things, not atoms, not power. The quantum information is in a grid though, a grid of ghosts. Even if nothing is said, that grid might still do something. Some physicists believe these quantum units could store information about what the universe was, what it did, what rules it obeyed. Like etchings on a stone tablet, the final state of the lattice might preserve the fingerprints of creation itself. Some ideas go even further and say that quantum lattices might be able to restart the world, in the same way that quantum fluctuations can make particles appear out of thin air. Space itself might be able to reorder itself or start a new growth, like when a game system starts over after a crash. The rules for making a new universe might still be in a universe that is broken and stuck. But the grid might be the only thing left, if there isn't a reboot. Things break down, light fades, and time crawls to a halt. What's left is order. The grid, the quiet reasoning that makes everything real. And it could be completely still. The world doesn't blow up in this version of the end. There is no freezing. This doesn't tear. It just stays the same, like an endless string of quantum cells that don't have any more energy to move. If space is made of tiny units and all activity ceases, what's the difference between a dead universe and an empty hard drive? Could something start it up one day? Could a small change or twitch in the grid cause a new Big Bang to happen? The grid may stay cold and still for all time. We're not sure. Of course, if quantum lattices are real, the universe might not end up being dark or full of dust. But building. Collapse of cosmic backgrounds when radiation ceases. The universe is full of soft, inaudible signs from the past that help us figure out where we came from. The cosmic background is made up of old light and particles that were around when the Big Bang happened and when stars were first formed. With their quiet stretches across space, they've been with us since the beginning. But they won't stay here for long. One day, there will be no more radiation at all. In this group, we will begin with the cosmic microwave background, CMB, which is the most well-known artifact. A light stream of microwave radiation fills all space. It's the glow left over from the Big Bang. It's about 2.7 degrees above 0 degrees right now. Cold, but not quiet. Billions of years ago, it was hotter and brighter, but as the universe expanded, the CMB cooled. Its photons got redshifted, stretched into longer and longer wavelengths. What was once blinding has become a low, uniform hum. The CMB will keep getting cooler in the very far future, and it will go away in the end. Photons don't really go away, they just lose energy. Their wavelengths get longer as space grows until they are so long and low in energy that they can't be seen at all. One photon could reach across a galaxy, then a supercluster, and finally the whole universe that we can see. It got to the point where even the sharpest detectors couldn't tell the difference between a photon that had been stretched and nothing. But the CMB isn't alone. There are other backgrounds too. The neutrino background, made of ghostly particles created seconds after the Big Bang. The gravitational wave background, born from early universe turbulence and black hole collisions. And the infrared, X-ray, and gamma-ray backgrounds, remnants from ancient galaxies and dying stars. All of these are going away. There is quiet between all of them. Neutrinos, for instance, used to be very energetic. Now they fly right through us without a trace, barely engaging. They will be spread out so far apart and moving so slowly in the far future that their energy will no longer be useful. A cloud of ghosts that can't be seen. Gravitational waves, ripples in space-time from collisions billions of years ago, are also losing power. They stretch with the universe. Their frequencies drop. Their impact fades. One day, the wave will be so long that even space-time doesn't feel the difference between its peaks and valleys. This is what happens when cosmic backgrounds fall apart. Not a crash, not a bomb going off, but a soft going away. A universe that is letting go of its past one photon at a time, from vibration to vibration. After that, what's left? Not light, not sound, don't stress, nothing but silence. Cosmic backgrounds are more than radiation. They're records. They tell the story of what happened. They hold fingerprints of ancient stars, galaxies, and even quantum fluctuations from the dawn of time. When they fall apart, the universe forgets about them. They are the only things that can tell us where we came from. There was no sound of the bang, not a trace of gravity, not any particle fossils. The canvas is now empty. The scariest part is that this happens before the person dies of heat. Dark clouds will cover the sky no matter how much matter or black holes are around. Not because things are broken, but because you can't see anything anymore. Subatomic time crystals patterns that defy entropy. If everything ended, time would slow down, matter would break down, and the world would be a ghost of what it used to be. You might think that nothing would be left, not a star, nothing moving. There is no order. What if, though, something still rang? These tiny time crystals could be the only beat in the world in the far future, when everything is completely dark. Atoms arrange themselves in space in designs that repeat in crystals that are regular, like snowflakes, diamonds, or salt. Over and over the same shape. Their structure stays the same. That's what makes them strong and steady. But in 2012, Nobel Prize-winning physicist Frank Wilczek asked, "What if there were crystals that repeated in time instead? Not just sitting still, but moving in a perfect loop, forever. No energy spent, no decay, just motion locked in an endless cycle." For a while it sounded impossible. The second law of thermodynamics says entropy always increases, things fall apart, order dissolves. There's no such thing as a perpetual motion machine. Then, in 2016, time diamonds really did exist. Physicists made them in very cold rooms by trapping atoms and carefully timing laser waves. These systems oscillated without any added energy. They weren't breaking any physics rules. Instead, they were using the strange rules of quantum mechanics to avoid entropy. Now imagine that idea taken to its cosmic extreme. Could natural time crystals exist? Not in labs, but in the coldest corners of space, or inside exotic forms of matter long after everything else has died. Could particles fall into repeating time-based patterns that never decay? Tiny quantum pendulums pulsing through the end of time? There are scientists who believe it's possible. Even when the world is very cold, some systems may settle into stable cycles at the subatomic level. It wasn't possible for these discrete time crystals to shine. They didn't heat up. They didn't want to make galaxies or stars. But they would always move in the same way. They would be like clocks that don't work in a place where time doesn't mean anything. In a universe where entropy has flattened everything, time crystals represent surviving order. A loophole that lets structure endure, even when the rules say it shouldn't. They're a rebel pattern, one last rhythm in a frozen sea. Could they be the last thing that makes things complicated? Could time rocks talk to each other? Would they be able to store data? Some scientists think that time crystals might be able to talk to each other in very rare situations, either through weak quantum interaction or by changing other subatomic fields. They might be like seeds, ready to grow into something more complicated or even start a new world. Echoes of inflation, traces from before the beginning. Before there were atoms, before dawn, there was inflation before time as we know it started. It happened so quickly, violently and mysteriously that it changed the whole world in a split second. And after the stars die, the black holes fade and matter disappears. The echoes of that moment in time may still be out there, etched into the very fabric of reality. There was something before the Big Bang. It was the hot, dense state that came after something even stranger, a burst of inflation in the universe. In the very first tiny fraction of a second after the beginning, or less than 105 seconds, space itself blew up, as space, not into space. There were points that grew bigger than the speed of light. Quantum fluctuations that were once very small were blown up to huge sizes. These changes are what made galaxies possible. They're what make the cosmic microwave background not totally smooth. The universe would be rough and uneven without inflation. It might not even have any life in it. But what inflation leaves behind is even stranger, because inflation wasn't just a process, it was a change from a state of high energy to the world we live in now. Everything calmed down, like a ball rolling down a steep hill into a small valley. But it left scars because of what it did. Noticeable marks, quantum waves. There are anisotropies in space. We can still see some of these today in the background radiation in the distribution of galaxies in gravitational waves. But those are just the loudest echoes, the most obvious ones. What if inflation left behind whispers? Patterns so deep and subtle that they outlive everything. Because the very first elements of the universe might still be present at a basic level in the very far future, after all the stars have died and all the matter has broken down. Not as matter or light, but as shape. Space itself may have a framework that was set in place by the inflating burst, a kind of rock from space. You might be able to see it if you could zoom out far enough or use the right tools. The way space curves. How it all fits together, a tiny sign of a process that took place before rules were made. Some physicists believe this imprint is embedded in the gravitational field, not in the particles we can see, but in the relationships between space and time. Even if no one is left to observe them, these patterns could persist like ripples frozen in a pond after the water has turned to ice. This is where things get crazy. In many models of inflation, especially endless inflation, the world we live in is just a bubble in a huge foam that is growing. There are rules of physics, standards, and fates that are unique to each bubble. But when bubbles form, they sometimes leave behind signs of where they hit each other. Gravitational warps happen, changes in density, a lot of strange patterns in the sky. If that's true, our universe may already have light marks on it from running into other bubble universes during inflation. What about those scars? They might not go away. These signs of inflation might still be in the underlying space-time grid even after everything else is gone, even after photons redshift into shadows that can't be seen and matter is reduced to a thin layer of particles. They would be hidden from you. They would still be there, though. They would be the oldest pieces of information known to man, not as new as light, not as new as matter. They could be the last ones. What does this mean for the end? It means that the world doesn't end and become nothing. It fades away into history. Not as we usually think of it, not memories, not data, not records, but memories that are built up over time. A frozen picture of the first explosion that caused everything. Some ideas even say that these marks of inflation might have an effect on what happens next. If the vacuum decays, if a new universe bubbles out of the remains of ours, these deep patterns might shape its birth. Like ripples in dough that guide the way it rises, inflationary echoes could define the architecture of the next reality. So the first moment of everything could also be the last thing that goes away. The inflation was a mess. Dangerous. Be creative. Those marks could be the only things that remind space of what it used to be in a world that is cold and empty. Entropy walls, zones of maximum disorder. The fate of the world is based on a simple rule. Entropy does not go down. Entropy is a way to measure how disorganized things are and how energy spreads out over time. In the end, the world will hit a point where nothing interesting can happen anymore. This is why ice melts and stars die. But what if entropy doesn't rise the same way everywhere? What if, near the end of time, the edges of chaos aren't smooth but instead look like strange broken lines? Huge areas of complete chaos. Things that stop chaos. This is not science fiction. It's a real, if hypothetical, question in the study of the universe today. Because things don't always get boring in the same way as the universe ages and entropy soars. In fact, certain parts of the world could get stuck in different thermodynamic states, with each one being like an entropic bubble. Consider that some parts of the universe change in very small ways. One patch quickly turns into a black hole. Another loses all of its stars and is quiet. A third stays in a strange particle phase because of changes in the quantum world. These areas become less similar over time. Their temps, particle masses, and energy levels start to be uneven. The time machine needs to be moved forward by trillions, quadrillions, and then Google years. The stars are gone. No more galaxies are being made. Black holes are going away. Decay of protons is happening. But what about entropy? Entropy is still at work, moving around the little energy that is left, evening out differences and smoothing out rough spots. Except, not everywhere. There was maximum entropy in some places before it happened in others. They turn into thermal dead zones, which are places where nothing can happen because everything is flat and balanced. There may still be black holes or small energy differences in other areas, which causes thermodynamic stress between them. There are what some thinkers are calling entropy walls, at the unseen lines where these regions meet. You can't see or touch these walls, so they're not real. One area of the room is more used up than another, so there are variations in the disorder. They still act like walls, though. Why? Because there is no movement across an entropy wall. Energy can't cross from one side to the other because there's no energy gradient left to drive it. Information can't travel because it gets scrambled by maximum entropy. Time barely means anything. because there's no change to mark its passage. In a way, entropy walls separate parts of the world and lock them up in thermodynamic jails that are quiet. No one knows about the others as they change on their own. Also, these areas are cut off even more if the universe keeps growing and dark energy keeps pushing space apart. The walls are long. More space opens up. There are cold islands in entropic zones where things break apart. Things get weirder though. Information and entropy are linked in some theories of quantum gravity. That means these entropy walls might separate parts of the world that can't remember each other, like memory boundaries. The universe seems to have forgotten how to be whole. We are now left with scattered, separate pieces of what used to be a single, united universe. Quantum mechanics allows for rare, low-probability events, even in high-entropy conditions. That means fluctuations could arise at the walls, tiny, brief reversals of entropy. Not enough to restart a universe, but maybe enough to create a fleeting blip of order. These tiny reversals might ripple along the boundary, creating entropic ripples, temporary phenomena that flash and fade without lasting consequence. But in a universe where nothing else happens, even a flicker matters. Are there chances of life in these areas? Almost certainly not. Entropy walls are bad for life. They show total balance, which means there are no changes, reactions, or useful energy. If there is still a time arrow, it doesn't point anywhere. But maybe the seeds of these areas were planted a very long time ago, billions or trillions of years ago. Differences in quanta, small imbalances. It's possible that the early structure of space-time already had the cracks that make up the end of everything written in it. Here's how to look at it. The Big Bang made things interesting, building, not balanced. That's what made stars, planets, and life possible. But the end of the universe might not mean that everything flattens into a grey soup. Instead, space might split into a patchwork of nothingness, with unseen walls of dead energy separating the pieces. The universe doesn't melt all at once. It breaks, and decay builds walls between the cracks. Ost Big Freeze scenarios, the reign of quantum nothing. For many, the Big Freeze is the classic slow-motion end of the world, not a fire. Nothing blows up. Everything is cooling down, stretching out, and moving more slowly until the universe is so empty and cold that nothing new can happen. Stars die. Things break down. Light stretches until it can't be seen. But here's the thing. The Big Freeze might not be the end of the story, because the world might not be dead after all, even when it's cold and quiet. It could be ready. The next chapter will be written by the strange, unseen hand of quantum physics. First, let's talk about what takes place after the Big Freeze. The timeline is mind-bending. We're talking trillions of years after the last star flickers out, after all white dwarfs cool into black dwarfs, after black holes evaporate into nothing, after protons fall apart and atoms cease to exist. All that remains are the loners of physics. Particles like neutrinos, some photons, perhaps a trace of dark matter, spread so far apart, so low in energy, they no longer interact in meaningful ways. This is the Big Freeze, maximum entropy, no gradients, no heat, no activity. Even if the world is completely dead and has no heat, quantum forces will still exist. The quantum field theory says that even empty space is not really empty. It's a foaming mess of uncertainty. Zero-point energy that jumps around with random, unpredictable changes. These are the rules of the world below the atoms. Just because everything else is quiet doesn't mean they turn off. So even after the Big Freeze, these quantum fields are still shaking, making virtual particles that appear and disappear every trillionth of a second. Most of these changes are not dangerous. They go off, then pop. But sometimes something bigger might happen. An event of quantum tunneling. A fake fall of the vacuum, a bubble of new science. Following the Big Freeze, this is where the reign of quantum nothing takes place. A time in the world when nothing should happen, but could. Let's look into what's possible. The vacuum decay situation is one of the most exciting ones. There is a possibility that our universe could fall into a true vacuum if it is in a false vacuum, which is a temporarily stable energy state. We've already talked about this. This would create a bubble of new physics, where the rules we take for granted, gravity, matter, even time, no longer apply. That bubble would expand at nearly the speed of light, rewriting everything in its path. After the Big Freeze, with no stars or galaxies to disrupt, such a bubble could grow unchallenged, erasing the old universe and replacing it with something new. In this view, the Big Freeze isn't the end. It's the setup for a new beginning. Another possibility is that quantum fluctuations could build up structure, particle by particle. Given infinite time, even highly improbable events become inevitable. It might take 10 circumflex 50 years, but eventually a fluctuation could produce something complex, a single atom, a small molecule, maybe even a self-replicating system. It's called a Boltzmann brain, a theoretical mind that randomly fluctuates into existence, complete with a memory of a life it never lived. Scientists debate whether this is plausible or just philosophical nonsense. But in the post-freeze universe, there's no rule that says it can't happen. Some hypothetical models say that quantum gravity effects might be able to make mini Big Bangs happen in the right circumstances. These would be tiny worlds that start to form inside the big frozen one. Each of these small worlds could grow into a full-fledged universe with its own rules, constants, and particles. Cosmic memory. Can a dead universe reboot itself? In this void of sound, what if the universe still holds a memory? What if there is a record of what it was like in the structure of space itself, not in light or matter? Also, what if that memory is the key to making everything new? Let's talk about cosmic memory, which is the idea that something stays even after chaos peaks and the last particle goes away. Not things you can touch, not physics, but there are still rules, patterns, and frames that show what the world was and what it could be again. We know that remembering things isn't always clear. Your steps are a memory when you walk across a snowy field. You can remember when a tree bends in the wind and never straightens out again. There are signs even when there are no live things left. Even after heat death, the final dissipation of usable energy, the laws of physics don't necessarily vanish. The quantum fields that underpin everything we know may still exist in the vacuum. They may be stretched, muted, near zero in energy, but they're still there. It's like the building's bones when the city is gone. Everything broke down. The decorations, the bricks, and the wires. The form is still in the base, though. In quantum coupling, we can see an example of this. It's strange how particles that used to be connected can stay connected over very long distances. They will always remember being connected in the web of quantum reality, even after they're no longer talking to each other. This means that the organization of information, who is linked to what and how, may last longer than the thing itself. What about the whole world, though? Could it remember something? There are some ideas that say yes. In loop quantum gravity, space is made up of separate loops, which are like the building blocks of geometry. The way these loops are arranged, how they twist, knot, and join, might hold a memory of things that happened in the past. This inner geometric structure might hold the past of the universe as matter breaks down and entropy spreads. It can't be read the way we read books. But it was still there, deep in the most basic parts of space-time. Holographic ideas are linked to other ideas. In these models, every particle and field in an area of space store their information not in the space itself, but on the edge of it. In other words, the edges of the universe could remember what happened inside even after it died. It's like finding a burned photo where you can just barely make out the picture in the ash. Now, let's say that the vacuum, which is thought to be empty space, isn't really empty. Quantum science tells us that vacuum is not the same as nothingness. It's buzzing with small, short-lived changes. Particles in the virtual world come and go. Fields shake, and maybe, just maybe, some of those changes are related to the old system. Something from the past might have changed the universe's default state, for that is where cosmic memory is more than just leftovers. It turns into possibility. When the vacuum shakes in just the right way, if the right change happens, those patterns could be used as a model for new order. Using its memories of the past, the world could, in a way, start over. It's not like playing back a tape. It wouldn't exactly copy our world. However, the basic rules, such as gravity, charge, and mass, may show up in similar ways. Patterns in the memory grid of empty space could change how new particles are made, how space grows, and even how time starts over. Not only can new worlds form from old ones, but they also form with similar properties because they are shaped by what came before. This is the dream of cosmic recursion. There may be fossils in our universe that come from a different time and place. It's possible that patterns in the cosmic microwave background, strange things that happen during inflation, and even the values of physical constants could be echoes or waves from a previous cycle. Then what will be there when the world ends? Not silence, not nothing, but shadows, patterns, and options that flicker in the dark. The end might not be a wall, but a change. This isn't just the end of the universe. There are black dwarf explosions, quantum foam rebirths, entropy's quiet grip, and gravity whispers beyond the speed of light. It's a plan of what might be in the ruins. Also, if the rules of science are still true, the story must go on somewhere. Do you want to keep following the world after it ends? Our team at Beyond Horizons is excited to start this new journey. Please like, follow, and turn on alerts.